Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and the universe takes its time unfolding, one gentle idea at a time. Wherever you happen to be listening from tonight, whether you're tucked into a quiet bedroom, resting on a late train ride, or simply letting the day fade away on a couch that knows your shape very well, I am glad you are here. There is something comforting about sharing a moment like this, even across great distances, and in a world that spins at such a relentless pace, it can be nice to slow down together and wander through a question that is far bigger than any of our daily worries. So let me ask you, just softly, without any pressure to answer out loud, where are you right now? And what time is it in your little corner of the world? Is the sky dark, dotted with stars, or is there still a hint of daylight clinging to the horizon? Perhaps you're listening in the early hours, when everything feels hushed and private. Or maybe it is the middle of the day and you are simply taking a quiet break from everything else that wants your attention. Either way, this space is yours for a while, and the only thing you need to do is listen, and let your thoughts drift gently along. Tonight, our slow journey is going to take us very, very far away from here. Not just across oceans or continents, but out beyond the air we breathe, past the moon that keeps our nights company, and deeper into a universe filled with objects so large and so powerful that the human mind has a hard time wrapping itself around them. We are going to explore a simple-sounding question that turns out to be anything but simple when you really sit with it. What is the largest star ever discovered in the universe? At first, that might sound like the sort of question you could answer with a quick number, a name, maybe a picture with a few arrows pointing at it. But the more you think about it, the more it starts to open up into something wider and more curious. What does it even mean for a star to be large? Are we talking about how heavy it is, how wide it stretches, how much light it gives off, or how much space it would take up if you could somehow place it next to our own sun? And how do we, standing here on a small planet that orbits one fairly ordinary star, manage to measure something that exists so far away that its light has been travelling for thousands of years just to reach our eyes? Before we drift into those details, it can help to start with something familiar. Think for a moment about the sun. Not the gentle, filtered version you might see through sunglasses or at sunset, but the real thing. A massive, glowing sphere of hot gas, so large that more than 1 million Earths could fit inside it. Even that fact alone is enough to make most people pause. 1 million worlds, all packed into a single ball of fire that still manages to look like a small, comfortable circle in our sky. The sun dominates our solar system. Its gravity holds every planet, every moon, every wandering rock in a kind of invisible embrace. It provides the energy that drives our weather, grows our food, and warms our oceans. For most of human history, it was the biggest, brightest, and most powerful thing we could easily see. And yet, as enormous as the sun is, it turns out to be something like a modest middle-of-the-road star when you compare it to what else is out there. Somewhere in the vast reaches of the Milky Way, and even farther beyond in other galaxies, there are stars that make our sun look small by comparison. Not just a little smaller, but almost difficult to spot if you could place them side by side in a cosmic lineup. The idea of something so large that it could swallow our entire solar system, planets and all, is one of those thoughts that can feel both thrilling and oddly calming. Thrilling, because it stretches your imagination beyond its usual limits. Calming, because it quietly reminds you that whatever feels overwhelming in your own life is, in a very literal sense, tiny when set against the scale of the universe. Now, if you find this kind of wandering through big ideas soothing, or if you simply enjoy having a gentle voice in the background while you unwind, you might consider liking this little corner of the internet or subscribing to it. It helps these calm, curious journeys reach other people who might need a quiet place to land at the end of a long day. There is no rush and no pressure, just something to keep in mind as we keep going. With that settled, let us start easing our way into the story of how humans began to realize that not all stars are created equal, and that some of them grow to sizes that almost defy description. long before anyone had telescopes, long before anyone knew that stars were distant suns rather than tiny holes in a crystal sky, people looked up and noticed patterns. They saw points of light that seemed steady and eternal, and they gave them names, stories, and personalities. Some stars were brighter than others. Some had a reddish tint. Some seemed to flicker, while others held their light more calmly. Even without understanding what stars actually were, ancient observers could tell that the night sky was not a flat, uniform sheet. When the first telescopes came along in the early 17th century, they began to peel back a little of that mystery. Stars that looked like single points to the naked eye sometimes turned out to be clusters. Faint smudges became entire galaxies, and over time, as instruments improved and physics advanced, scientists started to learn what stars are made of, how they shine, and how they live and die. At its simplest, a star is a huge ball of gas, mostly hydrogen, held together by gravity and powered by nuclear reactions in its core. Deep inside, immense pressure and heat force hydrogen atoms to fuse together into helium, releasing energy in the process. That energy works its way outward and eventually escapes as light and heat. This balance between the inward pull of gravity and the outward push of energy is what keeps a star stable for most of its life. But not all stars start out with the same amount of material. Some are born with relatively modest masses, just enough to ignite those nuclear reactions and glow quietly for billions of years. Others form in dense, crowded regions of space where huge clouds of gas and dust collapse into truly massive objects. These stars begin their lives with many times the mass of our Sun, and that extra material changes everything about how they behave. One of the first things it changes is how big they get. A more massive star has stronger gravity, which might sound like it would make it smaller and more compact. But it also has much more intense nuclear reactions at its core, producing far more energy. That energy pushes outward, inflating the star's outer layers and making it swell. As stars age, this process can become even more dramatic. When a star like our Sun eventually runs low on hydrogen in its core, it will begin to expand into a red giant, growing many times larger than it was in its stable, middle-aged phase. For stars that start out much more massive, this expansion can reach truly staggering proportions. These are the stars that astronomers call supergiants and hypergiants, and they are the ones that compete for the title of largest known star. So when we talk about the largest star, we usually mean the one with the greatest physical size, the one with the widest diameter, the one that would take up the most space if you could somehow place it in a cosmic measuring cup. This is different from the most massive star, which is about how much material it contains, or the brightest star, which is about how much light it gives off. A star can be incredibly massive but not particularly large in terms of diameter, and another can be enormous in size but not the heaviest in weight. This distinction matters because the stars that grow to the largest sizes are often in a particular stage of their lives. They're usually older, more evolved stars that have already burned through the hydrogen in their cores and are now fusing heavier elements in layers around the centre. This creates a complex internal structure, with different fusion processes happening at different depths, and it causes the star's outer layers to puff up like a slowly expanding balloon. Imagine a campfire that starts with a tight, bright flame, and then spreads out as you add more fuel and the heat pushes outward. The star is doing something similar, but on a scale so large that the comparison almost feels unfair. Now comes the part where things get especially interesting. How do we actually figure out how big one of these distant stars is? We cannot fly out to it with a measuring tape. We cannot even see its surface clearly in most cases. What we get is light, and from that light we have to work backward. Astronomers use a combination of techniques to estimate a star's size. One of the key pieces of information is its brightness, how much light it appears to give off. Another is its distance from us. which can be measured using methods like parallax, where scientists observe how a star's apparent position shifts slightly as Earth moves around the Sun. If you know how bright a star looks and how far away it is, you can calculate how much light it is actually producing. Then, by understanding the physics of how stars emit light at different temperatures, astronomers can estimate the star's surface temperature. Once you have both the total amount of light and the temperature, you can use a law of physics known as the Stephenson-Boltzmann law to work out how large the star must be to produce that much light at that temperature. It is a bit like standing far away from a campfire on a cold night. If you know how warm you feel and how far away you are, you can make a reasonable guess about how big the fire is, even if you cannot see every log and ember. Of course, this process is not perfect. There are uncertainties in the distance measurements, variations in how stars behave, and complications like dust and gas between us and the star that can dim or redden the light. That means that when astronomers talk about the size of the largest star, they usually include a margin of error. It is not a single exact number carved into a cosmic stone tablet. It is an estimate, refined over time as better data comes in. For a while, different stars held the unofficial title of largest known. As telescopes improved and surveys expanded, new candidates appeared. Some stars that were once thought to be record holders turned out to be smaller than originally believed when their distances were measured more accurately. Others rose in the rankings as new observations revealed just how far their outer layers extended. One of the reasons this is so tricky is that the largest stars often have very diffuse outer atmospheres. Their edges are not sharp and well defined like a solid object. Instead, their gas becomes thinner and thinner as you move outward, blending gradually into the surrounding space. So where exactly does the star end and the rest of the universe begin? Different definitions can lead to slightly different answers. Still, even with all those uncertainties, there is one star that has become something of a favourite in conversations about cosmic size. It goes by the name UY Scuti. UY Scuti is a red supergiant located in the Milky Way galaxy, in the direction of the constellation Scutum, which is a small and relatively faint pattern of stars in the night sky. You cannot see UY Scuti with your naked eye. It is too far away and too dim from our perspective, despite its enormous size. But when astronomers studied it more closely, they realized that it is one of the largest stars ever measured. To give you a sense of scale, imagine placing UY Scuti at the centre of our solar system, where the Sun currently sits. Its outer edge would extend well beyond the orbit of Jupiter, possibly even approaching the region where Saturn travels. Mercury, Venus, Earth, Mars, the asteroid belt and the giant gas planets up to Jupiter would all be inside the star's vast glowing envelope. It is hard to picture that kind of size in a meaningful way, because our everyday experiences do not include anything remotely comparable. Even the largest structures humans have ever built are tiny dots next to a planet, let alone a star that could swallow multiple planetary orbits whole. But UY Scuti is not alone in this category. There are other red supergiants and hypergiants that come close to its estimated size, and in some cases the uncertainties in the measurements mean that the exact ranking can shift. Stars like VFI Canis Majoris, Westerlund 1-26, and a few others have all been contenders for the title at different times. This leads to a gentle but important point. When we talk about the largest star ever discovered, we're really talking about the largest star we currently know about, based on the best measurements we have so far. The universe is vast beyond easy comprehension, and our galaxy alone contains hundreds of billions of stars. Beyond that, there are billions of other galaxies. It would be surprising if we had already found the absolute biggest example of something as common as a star. So in a way, the question is not just about one specific object. It is also about our ongoing search, our methods, and our growing ability to explore deeper and farther into space. As you let that idea settle, you might notice how your breathing naturally slows when you think about things on this scale. There is something about contemplating enormous distances and immense objects that can make the small, immediate concerns of the day feel a little lighter. You do not have to solve anything right now. You do not have to reach any conclusions. You can simply let the picture form in your mind. A vast, quiet universe filled with glowing spheres of gas, some small and steady, others bloated and nearing the end of their lives, all of them drifting through space on timescales that make human history look like a brief flicker. Long before anyone had words like galaxy, fusion, or light years, people were already tilting their heads back and staring into the dark. You can picture it if you like, a group of early humans gathered around a low, flickering fire, the sky above them stretching endlessly, scattered with small points of light that seemed both close enough to touch and impossibly far away. There were no maps of the heavens, no explanations written in books, just the quiet sense that something vast and mysterious was hanging overhead, night after night, year after year. It is interesting to notice how natural that upward glance feels. Even today, in cities where the stars are mostly hidden behind streetlights and glowing windows, people still find themselves looking up. Maybe it happens when a plane crosses the sky, or when the moon is unusually bright, or when a sudden break in the clouds reveals a few steady stars. There is a pause, sometimes just a second, where the mind seems to open a little wider. The world feels larger. The moment feels slower. That instinct to look toward the biggest things did not start with telescopes or science. It seems to be woven into the way humans experience the world. The sky is the largest visible feature in our daily lives. It arches over every landscape, every ocean, every city and forest. You can walk for hours, travel across countries, cross seas, and still, when you stop and look up, it is there, unchanged in its broad, quiet presence. For early humans, the sky was not just something to admire. It was a guide, a calendar, and a source of stories. The rising and setting of the sun marked the rhythm of day and night. The changing shape of the moon gave a sense of passing weeks. The slow shifting of constellations across the seasons hinted at a larger cycle, one that tied the sky to the growth of plants, the movement of animals, and the timing of migrations and harvests. When you think about it, it makes sense that the biggest things in view became the anchors for meaning. A mountain, a river, the ocean, and above all, the sky. These were the features that seemed permanent in a world that was otherwise full of change. Trees grew and fell, camps were moved, people were born and died. But the stars returned each night, familiar in their patterns, steady in their quiet light. Across different cultures and continents, humans began to connect those patterns into stories. In one place, a cluster of stars might become a hunter. In another, the same stars might be seen as a boat, an animal, or a group of ancestors watching from above. These stories were not just entertainment. They were ways of remembering the sky, of passing knowledge from one generation to the next, and of making the vastness overhead feel a little more personal. There is something deeply human about turning the biggest, most distant things into something relatable. It is as if, by naming them and telling stories about them, people could bring the sky a little closer, make it less intimidating, more like a shared home than an unreachable ceiling. Over time, that sense of wonder began to mix with curiosity. People did not just want to know what the stars represented in stories, they wanted to know what they actually were. Why did some move across the sky while others stayed fixed? Why did some shine more brightly than others? Why did certain patterns only appear at certain times of the year? This shift from storytelling to systematic observation did not happen all at once, and it did not replace the old stories so much as sit alongside them. In ancient Mesopotamia, priests carefully recorded the positions of stars and planets on clay tablets. In ancient Egypt, the movement of the stars was tied to the flooding of the Nile and the timing of agricultural cycles. In China, detailed star catalogues were created, mapping the sky with remarkable precision. In these early efforts, the biggest things in the sky were often the most important. The sun and moon were obvious focal points. The planets, which moved differently from the fixed stars, drew special attention, and certain bright stars became markers, reference points in the slow turning dome of the heavens. As centuries passed and tools improved, humans began to extend their reach beyond what the naked eye could see. The invention of the telescope was a turning point. Suddenly the sky was not just a flat backdrop of points of light. It became a landscape with depth. Stars varied in colour and brightness. Faint, cloudy patches turned out to be clusters of countless stars or distant galaxies. The moon revealed mountains and craters. Jupiter showed moons of its own. With each new discovery, the sense of scale grew. The Earth was no longer the centre of everything. The sun was not just a light in the sky, but a star among many. The Milky Way was not the whole universe, but one galaxy in a vast sea of others. In this expanding picture, the idea of big took on new meaning. A mountain that once seemed enormous now felt small compared to a planet. A planet felt small compared to a star. A star felt small compared to a galaxy. And a galaxy felt like just one part of something even larger. Still, even as the scale increased, the human mind kept returning to comparisons. How big is this compared to that? How far away is that compared to here? How long would it take to travel from one place to another? These questions are not just scientific, they are also deeply personal. They help us locate ourselves in a universe that can otherwise feel overwhelmingly vast. This is where the fascination with the largest things becomes especially clear. When people ask about the biggest mountain, the deepest ocean trench, the tallest building, or the largest star, they are not just looking for a fact. They are looking for a boundary, a kind of edge to their understanding. Where does big stop? How far does it go before it becomes something almost unimaginable? In the case of stars, this curiosity is amplified by the fact that stars are both familiar and alien. We live under one every day. We feel its warmth. We rely on its light. And yet, we cannot approach it. We cannot touch it. We cannot visit it in any practical sense. It is close enough to matter deeply in our lives, but far enough to remain out of reach. So when we hear about a star that is not just bigger than the sun, but so much bigger that it could contain the orbits of multiple planets, it triggers a particular kind of wonder. It takes something we think we know and stretches it beyond its usual limits. There is also a psychological side to this attraction to the biggest things. Humans are by nature storytellers. We think in terms of beginnings, middles and ends. We look for heroes, challenges and climaxes. In the natural world, extremes often play that role. The highest, the deepest, the fastest, the oldest, the biggest. These become the landmarks of our understanding, the points we use to organise everything else. In a way, the largest star becomes a kind of character in the story of the universe. It represents the upper end of what stars can be, a living example of how far the process of star formation and evolution can go before it reaches its limits. There is also something quietly comforting about knowing that there are things so large and so powerful that they exist completely outside the concerns of everyday life. A massive star does not care about deadlines, traffic, or unanswered messages. It does not notice our routines or our worries. It follows its own path shaped by gravity, pressure, and nuclear reactions, playing out over millions of years. Thinking about that can create a sense of perspective. It does not make personal problems disappear, but it can soften their edges, remind us that our lives, while important to us, are part of a much bigger picture. At the same time, humans do not just look at the biggest things from a distance. We also try to understand them, measure them, and place them into systems of knowledge. This is where the tools of science come in. Telescopes, satellites, spectroscopes, and computer models allow us to gather information from light that has travelled across space for vast stretches of time. Every photon that reaches a telescope carries a tiny piece of a star's story. Its colour can tell us about temperature. Its spectrum can reveal what elements are present. Its brightness, combined with distance measurements, can help us estimate size and energy output. So when astronomers identify a candidate for the largest known star, they are not just pointing at a dot in the sky and making a guess. They are building a picture from layers of data, checking it against physical laws, and comparing it to other known objects. This process itself reflects a very human trait. We are not satisfied with simply being impressed. We want to know how things work. We want to understand the rules that govern even the most distant and enormous parts of the universe. It is worth noticing how this blend of wonder and analysis has been present throughout history. Ancient sky watchers were careful observers, even as they told stories about gods and heroes in the stars. Modern astronomers use advanced mathematics and technology, but many of them still speak about the sky with a sense of awe. The language changes, the tools change. The feeling of looking up at something far larger than yourself and feeling both small and connected at the same time remains. There is also a social side to this fascination. Big discoveries tend to bring people together. When a new image from a space telescope is released, showing a nebula or a distant galaxy in vivid detail, it spreads quickly. People share it, talk about it, set it as their background. For a moment, many different lives intersect around the same picture of something vast and beautiful. Stories about the largest star or the farthest galaxy become part of this shared experience. They give people a common reference point, something to marvel at together, even if they are separated by thousands of miles. In a quieter, more personal way, these ideas can also shape how individuals think about their own lives. For some, the vastness of the universe brings a sense of humility. For others, it brings a sense of belonging, a feeling that being made of the same elements as stars connects them to something much larger than themselves. It is interesting how often people turn to the sky in moments of reflection. During times of celebration, they watch fireworks explode against the dark. During times of grief, they may find themselves staring at the stars, thinking about distance, time, and continuity. The biggest things in the universe become a kind of backdrop for the biggest moments in human life. As science has progressed, the questions have grown more detailed, but the core impulse remains the same. We look up. We notice something that feels larger than us. We wonder what it is, how it came to be, and what it means for our place in the world. When the topic turns to the largest star ever discovered, it taps into all of these layers at once. There is the simple, almost playful curiosity of wanting to know the answer. There is the technical challenge of measuring and comparing objects at incredible distances. There is the emotional response of imagining something so large that it reshapes your sense of scale. And there is the deeper, quieter reflection that comes from realizing that even the largest star is, in its own way, just one part of a universe that has no clear edge we can point to and say, this is where it ends. You might notice, as you sit with these ideas, how they create a certain mental spaciousness. Thoughts slow down. The mind drifts. It becomes easier to let go of the tight focus on immediate tasks and instead rest in a broader, softer awareness. This is one of the reasons that looking at the biggest things can feel calming rather than overwhelming. When you step back far enough, the small details that usually demand your attention start to blend into a wider view. The mental landscape becomes less crowded. What does largest actually mean when we're talking about stars? How do scientists define it, measure it, and compare one star to another? What kinds of stars tend to grow to enormous sizes, and what is happening inside them as they do? When someone hears the phrase largest star, it is very easy to picture a simple contest, as if all the stars in the universe lined up somewhere in the dark and we walked along them with a measuring stick, tapping each one and writing down a number. The biggest number wins, the title is handed out, and the question is neatly closed. But in practice, and in reality, the idea of largest turns out to be more like a gentle conversation than a single sharp answer. It depends on what you're really asking, and it depends on how you choose to listen to what the universe is telling you. To begin with, it helps to slow down and notice how often we use the word large in everyday life. A large cup of coffee, a large building, a large crowd. Sometimes we mean tall, sometimes we mean wide, sometimes we mean heavy, sometimes we mean powerful. The word stretches to fit whatever context we place it in. When we carry that same word into astronomy, it brings its flexibility with it. A star can be large in more than one way. It can be large in mass, meaning it contains a lot of material. It can be large in volume, meaning it takes up a lot of space. It can be large in brightness, meaning it gives off a great deal of energy and light. These qualities often overlap, but they are not the same thing, and they do not always travel together. Imagine two balloons. One is filled with water. It is heavy, dense, and compact. The other is filled with air. It is light, fluffy, and takes up a lot of room. If you asked which one is larger, you might get different answers depending on whether you're thinking about weight or size. Stars can be a bit like that. Some stars are incredibly massive but relatively compact. Others are enormous in size but surprisingly low in density. Their outer layers spread thinly across vast distances. When astronomers talk about the larger star, they are almost always referring to size in terms of physical diameter or radius, how far the star's surface extends from its centre, rather than how much it weighs. This distinction matters because the processes that make a star heavy are not always the same ones that make it swell. At the heart of every star is a balancing act. Gravity pulls inward, trying to compress all that gas into a smaller and smaller space. At the same time, energy produced by nuclear reactions in the core pushes outward, creating pressure that resists that collapse. For most of a star's life, these two forces are in a kind of truce, holding the star in a stable shape and size. When a star is born, it forms from a cloud of gas and dust that collapses under its own gravity. The more material in that cloud, the more massive the star that forms. A star that starts its life with a great deal of mass has a stronger gravitational pull, but it also has more fuel in its core, which leads to more intense nuclear reactions. That increased energy output pushes outward more forcefully, often causing the star's outer layers to expand. As the star ages, this balance can shift. When the hydrogen in the core begins to run low, the core contracts and heats up, while the outer layers expand and cool. The star enters a new phase of its life, becoming what astronomers call a giant or supergiant. In this stage, the star's radius can grow dramatically, sometimes by hundreds or even thousands of times its original size. This is one of the main ways stars become physically large. They do not start that way, they grow into it. So when we ask what the largest star is, we're usually looking for a star that has reached one of these late-life swollen phases and has expanded to an extraordinary degree. The star's mass may still be great, but its size is now dominated by a vast extended atmosphere of hot gas that reaches far into space. Another subtle point comes from the idea of where a star actually ends. Unlike a planet or a rock, a star does not have a solid surface you can point to and say, "This is the edge." Instead, it has layers of gas that become thinner and thinner as you move outward. The light we see usually comes from a region called the photosphere, which is where the star becomes opaque enough for light to escape into space. Beyond that, there are more layers, like the chromosphere and the corona, where the gas is extremely thin and faint. Depending on how you define the star's boundary, you can get slightly different measurements for its size. Most astronomers use the radius of the photosphere as the standard, because it is the most consistent and observable reference point. Even with that standard in place, measuring a star's radius is not as straightforward as measuring the radius of a planet. Stars are so far away that for most of them, they appear as points of light, even through powerful telescopes. Their disks are too small and too distant to be resolved directly, except for a few nearby giants that can be imaged with special techniques. So instead of seeing the star's edge, astronomers infer its size using indirect methods. One of the most important tools is the relationship between a star's brightness, temperature, and size. Every star emits energy. The total amount of energy it emits per second is called its luminosity. If you know how hot the star's surface is and how much energy it is putting out, you can calculate how large the surface must be to produce that energy at that temperature. This is based on well-tested physical laws that describe how hot objects radiate light. The process goes something like this. First, astronomers measure how bright the star appears from Earth. Then, they determine how far away it is. Distance is crucial, because a nearby dim star can look just as bright as a faraway powerful one. By knowing the distance, they can calculate the star's true luminosity. Next, they analyse the star's light with a spectroscope, which spreads the light into a spectrum of colours. This reveals information about the star's temperature and chemical composition. Once the temperature is known and the luminosity is known, the size can be worked out. This method is elegant, but it relies on accurate distance measurements. If the distance is slightly off, the calculated size can be significantly wrong. For many of the largest stars, distance is one of the hardest things to measure precisely, because they are often far away and surrounded by clouds of gas and dust that can distort or dim their light. That is one reason why the list of largest known stars has changed over time. As new data comes in and distances are refined, some stars move up the list and others move down. What was once thought to be the largest may turn out to be a little smaller than originally believed, while another star may take its place. There is also the question of variability. Many of the largest stars are not stable in the way our Sun is. They pulsate. Their outer layers expand and contract over time. This means their size can change, sometimes significantly, over periods of months or years. So when someone says a particular star is, for example, 1,700 times the radius of the Sun, that number may represent an average, or a measurement taken at a particular point in the star's cycle. At another time, it might be somewhat smaller or somewhat larger. This brings a kind of living quality to the idea of size. The largest stars are not static monuments. They are dynamic, restless objects, constantly shifting and shedding material into the space around them. Another layer to this question comes from the difference between size and influence. A star that is physically enormous may not necessarily be the most powerful in terms of gravity or energy output. Some very large stars are relatively cool on their surfaces, giving them a reddish colour. Their light is spread over a huge area, which can make them less intense per unit of surface than smaller, hotter stars. On the other hand, some smaller stars can be incredibly dense and energetic. Neutron stars, for example, are the remnants of massive stars that have exploded in supernovae. They are only about the size of a city, but they contain more mass than the Sun. They are not large in the sense of volume, but they are extreme in almost every other way. This contrast helps highlight why largest needs careful definition. In everyday language, large often implies impressive or powerful. In astronomy, those qualities can be separated. A star can be impressive because of its size, or because of its mass, or because of its brightness, or because of its role in shaping its surroundings. When we narrow the focus to physical size, we're really asking about stars that have reached a particular stage in their evolution, where they have expanded into giants or supergiants. These stars are often nearing the end of their lives. They have burned through much of their original fuel and are now fusing heavier elements in shells around their cores. This process creates an onion-like structure inside the star, with different layers fusing different elements. Each layer produces energy that contributes to the outward pressure, inflating the star's outer atmosphere. Over time, the star can lose material through strong stellar winds, creating vast clouds of gas around it. These surrounding clouds can make it even harder to define the star's boundary, because the transition from star to space becomes blurred. Light from the star can be scattered and absorbed by this material, complicating measurements. So, in a very real sense, the largest stars are also some of the most difficult to measure and understand. They sit at the edge of what we can observe clearly, both because of their distance and because of their complex changing nature. There is also the broader context of where these stars fit in the universe. The Milky Way galaxy alone contains hundreds of billions of stars. Most of them are small, dim, and relatively unremarkable. The giants and supergiants are rare. They form in regions where there is enough material to create very massive stars in the first place. These regions are often dense, active areas of star formation, filled with bright nebulae and clusters of young stars. The largest stars tend to live fast and die young, on cosmic timescales. While a star like the Sun can shine steadily for about 10 billion years, a very massive star might only last a few million years before it exhausts its fuel and ends its life in a dramatic explosion. So when we talk about the largest star ever discovered, we're also talking about something temporary. The star we point to today as the record holder is not a permanent feature of the universe. It is a moment in a long ongoing process of birth, growth, and destruction. This adds a quiet sense of movement to the question. The universe is not a static gallery of objects with fixed labels. It is a place where things are constantly changing, even on scales that feel impossibly slow to us. Another thought that sometimes comes up is whether there is a theoretical limit to how large a star can get. Physics does place some constraints. If a star becomes too massive, its own gravity can lead to instability. Radiation pressure from the intense energy output can push material away, limiting how much mass the star can hold on to. These competing forces mean that there is a range of sizes and masses that stars can occupy. The largest stars we observe are likely close to the upper edge of what is physically possible, but that edge is not a sharp, clearly marked line. It is more like a region of balance, where stars can exist for a while before the forces within them push them toward their final stages. When people hear about a star that is thousands of times larger than the Sun, it can be tempting to imagine it as a single solid thing, like a gigantic ball you could somehow walk around. In reality, these stars are more like enormous glowing clouds, with density so low in their outer layers that, if you could somehow stand there, you would not feel anything solid at all. You would be surrounded by a thin, hot gas, more like an extremely sparse fog than a surface. This idea can shift how you think about size. The largest stars are not just big in the way a mountain or a building is big. They are big in a more diffuse, extended way, spreading their presence across a vast region of space. So when we ask what we actually mean by largest star, we are really opening a door into a set of choices and definitions. We choose to focus on physical radius. We choose a particular way of defining the star's edge. We choose a method for measuring distance, brightness, and temperature. Each of these choices shapes the answer we get. That does not make the answer meaningless. It just makes it part of an ongoing conversation between human curiosity and the universe's complexity. There is something quietly fitting about that. The stars themselves are not fixed, and our understanding of them is not fixed either. Both are in motion, changing over time. As you sit with this idea, you might notice how it mirrors other parts of life. So many things that seem simple at first become richer and more layered the longer you look at them. A word, a memory, a place, or even a question can open up into something much larger than you expected. In the gentle space we're creating here, the question of the largest star becomes less about winning a cosmic contest and more about appreciating the process of looking, measuring, and wondering. It becomes a way to engage with the universe, not just as a collection of facts, but as a living system that invites attention and patience. Trying to measure something as enormous as a star that exists hundreds or thousands of light years away can feel a bit like trying to work out the size of a distant mountain while standing in thick fog, with nothing but its silhouette and a few scattered clues to guide you. Astronomers never get to walk up to these stars, never get to circle them, never get to touch their surfaces. Everything they know comes from light, faint, ancient light that has travelled across space for an almost unimaginable length of time before finally reaching a telescope. That simple fact shapes everything about how stellar sizes are measured. Light is the messenger, and astronomers have learned, patiently and carefully, how to listen to what it is saying. The first challenge is distance. Size cannot be separated from distance. A small star that is close can appear brighter than a huge star that is far away. To untangle that confusion, astronomers must first determine how far a star is from Earth. Without distance, brightness alone is misleading. One of the oldest and still most reliable methods for measuring stellar distance is parallax. It is based on a simple idea that you may have noticed without realizing it. Hold your thumb out in front of you and close one eye, then switch to the other eye. Your thumb appears to jump slightly against the background. That shift happens because your eyes are in different positions. Earth does the same thing as it orbits the Sun. Astronomers observe a nearby star at one point in Earth's orbit, then again 6 months later from the opposite side of the orbit. Against the far more distant background stars, the nearby star appears to shift ever so slightly. The angle of that shift, tiny though it is, allows astronomers to calculate the star's distance using geometry. For nearby stars, this method works beautifully. For very distant stars, especially the giant ones we're interested in, the shift becomes so small that it is extremely difficult to measure. This is where modern space missions such as Gaia have made a dramatic difference. Gaia measures stellar positions with extraordinary precision, refining distances for millions of stars and quietly reshuffling our understanding of which stars are truly as large as we thought. Once distance is known, the next step is figuring out how much light the star is actually producing. This is called luminosity. Astronomers start by measuring how bright the star appears from Earth. Then, using the distance, they calculate how bright it must be at the source to appear that way from so far away. Think of it like seeing a distant lighthouse across the sea. A dim light nearby and a powerful light far away might look similar at first glance. Knowing the distance lets you work backward to determine how strong the lamp must really be, but brightness alone still does not tell you size. A small, extremely hot object can shine just as brightly as a large, cooler one. This is where temperature enters the picture. To measure a star's temperature, astronomers study its spectrum. When starlight is passed through a prism or a diffraction grating, it spreads out into a rainbow of colours crossed by dark absorption lines. These lines act like fingerprints. They reveal which elements are present in the star's atmosphere and how hot that atmosphere is. Hotter stars peak in blue or white light. Cooler stars glow more toward red. Red supergiants, the class that includes many of the largest known stars, have relatively cool surface temperatures, even though their interiors are unimaginably hot. Their enormous size spreads that energy over a vast area, lowering the surface temperature and giving them their distinctive reddish appearance. Once astronomers know a star's luminosity and surface temperature, they can use a fundamental physical relationship to calculate its size. This relationship describes how the total energy radiated by an object depends on its temperature and surface area. In simple terms, if a star is very bright but not very hot, it must have a very large surface area. That surface area translates directly into radius. This calculation is the backbone of most stellar size estimates, especially for stars too distant to resolve directly. However, astronomers are not limited to indirect methods alone. For a small number of nearby giant stars, it is possible to measure their apparent size directly using a technique called interferometry. This involves combining light from multiple telescopes spread far apart to simulate a single, much larger telescope. By doing this, astronomers can resolve the disk of a star and measure its angular diameter, the tiny angle it occupies in the sky. Once the angular diameter is known, distance again becomes the key. With distance and angular size, the physical size can be calculated. This method has been used to measure the sizes of some red giants, and supergiants, confirming and refining the estimates obtained through luminosity and temperature. But even this method has its complications. The surfaces of giant stars are not smooth. They are dynamic, boiling with enormous convection cells, each one larger than the entire sun. Bright regions and darker patches can distort measurements, making the star appear larger or smaller, depending on when and how it is observed. There is also the issue of extended atmospheres. The largest stars often lose mass through powerful stellar winds, creating vast envelopes of gas around them. Some measurements capture light from deeper layers, while others include contributions from these extended regions. Deciding where the surface ends becomes a matter of definition rather than a clear physical boundary. Another tool astronomers use is variability. Many giant stars pulsate. They expand and contract rhythmically, causing their brightness and spectral features to change over time. By studying these changes, astronomers can learn about the star's internal structure and, in some cases, estimate its size more accurately. Pulsations act like a kind of stellar heartbeat. The timing and strength of those pulses are linked to the star's mass, radius, and internal processes. By listening carefully to that rhythm, astronomers gain another piece of the puzzle. Dust adds yet another layer of complexity. Many of the largest stars are surrounded by clouds of dust formed from material the star itself has shed. This dust absorbs and scatters light, making the star appear dimmer and redder than it really is. If not properly accounted for, dust can lead to underestimating a star's luminosity and, by extension, its size. To correct for this, astronomers observe stars across many wavelengths, not just visible light. Infrared observations are especially valuable because infrared light passes more easily through dust. By comparing measurements across different parts of the spectrum, scientists can reconstruct a clearer picture of the star's true output. Computer models play a crucial role in all of this. Observations provide data, but models connect that data to physical reality. By simulating how stars of different masses and compositions evolve over time, astronomers can test whether their measurements make sense. If a star appears to be extremely large but the model says such a star should be unstable or short-lived, that discrepancy prompts closer scrutiny. This back and forth between observation and theory is constant. A star might initially be reported as having an enormous radius, only for later studies to revise that estimate downward after improved distance measurements or better dust corrections. The list of largest known stars has changed many times as a result. It is important to understand that this is not a sign of failure. It is a sign of science doing exactly what it is supposed to do. Knowledge improves as tools improve. Estimates become more refined. Uncertainties shrink, even if they never disappear entirely. There is also an element of humility in this process. Astronomers are well aware that they are working at the limits of what can be measured. When they publish a size estimate for a distant supergiant, it often comes with error bars that acknowledge a range of possible values. The star might be a little smaller or a little larger than the central estimate suggests. In the case of the larger stars, those uncertainties can be significant, sometimes hundreds of times the radius of the Sun. That means that two stars may appear to compete for the title of largest, with overlapping uncertainty ranges. In such cases, it is not always possible to declare a single, definitive winner. This is why discussions of the largest star often include phrases like "one of the largest known," rather than absolute statements. The universe does not hand out neat trophies, it offers hints, patterns, and probabilities. Another fascinating aspect of measuring enormous stars is how much information can be extracted from such small signals. The light reaching Earth from a distant supergiant may have travelled for thousands of years, spreading out across space until only a tiny fraction reaches a telescope mirror. Yet within that faint glow is encoded the star's temperature, composition, motion, and size. It is a quiet triumph of human ingenuity that we can decode that information at all. From a practical standpoint, it means building instruments capable of extraordinary sensitivity and stability. From a conceptual standpoint, it means trusting that the laws of physics discovered in laboratories on Earth apply just as well to stars across the galaxy. As measurements improve, so does our understanding of stellar evolution. Knowing the true sizes of the largest stars helps astronomers test theories about how stars lose mass, how they transport energy, and how they ultimately die. These stars play an outsized role in shaping their environments. Their winds enrich surrounding space with heavy elements. Their eventual explosions seed future generations of stars and planets. So measuring their size is not just about satisfying curiosity, it is about understanding the life cycle of matter in the universe. There is also something quietly poetic about the fact that the largest stars are among the hardest to measure. Their sheer scale makes them elusive. They resist simple description. They require patience, collaboration, and a willingness to revise conclusions. This mirrors, in a way, how humans often relate to the biggest ideas in life. The most expansive questions about existence, time, and meaning are rarely answered all at once. They are approached gradually from different angles, with each new insight adding depth rather than closure. As you listen to how astronomers piece together the sizes of these distant giants, you might notice a similar slowing of perspective. The process unfolds over years and decades. Data accumulates, interpretations shift, understanding grows, but never snaps into a final fixed form. How do stars of different sizes compare? What does a truly enormous star look like when set alongside smaller ones? How wide is the range between the smallest stars and the largest ones we know? If you imagine the universe as a kind of quiet gallery, filled with countless glowing spheres drifting through dark, open halls, then taking a tour of stellar sizes is a bit like walking from one end of that gallery to the other, noticing how the exhibits slowly, steadily change. At one end, the stars are small, steady, and unassuming. At the other, they are vast, swollen, and almost difficult to take in all at once. The journey between those two extremes is not just a matter of numbers. It is a story about how stars live, grow, and sometimes transform into something very different from what they once were. It can be comforting to begin with something modest, something that does not immediately overwhelm the imagination. The smallest stars in the universe are known as red dwarfs. These are the quiet workers of the cosmic population. They are small, cool, and faint compared to stars like our Sun, but they are also incredibly common. In fact, most of the stars in the Milky Way are red dwarfs. A red dwarf might be only a fraction of the Sun's size and mass. Some are just large enough to sustain the nuclear reactions that make a star in the first place. Their light is gentle and reddish, and from a distance they can be easy to overlook. But what they lack in drama, they make up for in endurance. Red dwarfs burn their fuel slowly and efficiently, which means they can shine for hundreds of billions, even trillions of years. The universe is not old enough yet for any red dwarf to have naturally reached the end of its life. There is something quietly reassuring about that. These small stars are in no hurry. They glow steadily, almost patiently, as galaxies evolve around them. Moving a step up in size brings us to stars that are still considered small by cosmic standards, but feel more familiar. This is where our Sun lives. The Sun is classified as a main sequence star, which means it is in the stable phase of its life, fusing hydrogen into helium in its core and maintaining a balance between gravity and outward pressure. In terms of diameter, the Sun is about 1.4 million kilometres across. That number is already far beyond everyday scales. You could line up more than 100 Earths side by side across the Sun's face, and yet, in the grand tour of stellar sizes, the Sun sits somewhere near the middle, not at the top. There are stars a bit larger than the Sun, known as subgiants and giants. These are stars that have begun to change. They have used up much of the hydrogen in their cores and are starting to burn other fuels in surrounding layers. As a result, their outer regions expand, and their surface temperatures drop slightly, giving them a warmer, more orange or red appearance. These stars can be several times, or even dozens of times, larger than the Sun. If one of them were placed at the centre of our solar system, it might reach out to swallow the inner planets. Mercury and Venus would be lost inside its glowing atmosphere, and Earth might find itself skimming the edge. This is often the stage people picture when they hear about the future of the Sun. In about 5 billion years, our own star is expected to expand into a red giant, growing large enough to engulf at least the innermost planets. It is a reminder that size in the universe is not always a starting point. Sometimes it is a destination. Continuing along the scale, we reach the realm of supergiants. These are stars that began their lives with much more mass than the Sun. Their cores burn hotter and faster, and their lives are shorter and more intense. When they expand, they do so on a truly impressive scale. A red supergiant can be hundreds or even over 1,000 times the radius of the Sun. These stars are so large that, if you could place one where the Sun is now, its surface would extend far beyond the orbit of Mars, possibly out to the region where the asteroid belt lies. Despite their immense size, their outer layers are incredibly thin. The gas in those regions is so sparse that, compared to the air you breathe, it would feel like a near vacuum. The star's light emerges from a vast, gently glowing cloud rather than a solid surface. This combination of size and delicacy gives supergiants a somewhat fragile quality. They are enormous, but they are also unstable. Their outer layers can ripple and pulse. They lose mass in powerful winds, shedding material into the space around them. Over time, they create enormous shells and nebulae, marking their presence long after their light has faded. Among the supergiants, there is an even more extreme category often referred to as hypergiants. These stars push the boundaries of what stellar physics allows. They are incredibly luminous, unstable, and rare. Their sizes can rival or exceed those of the largest red supergiants, and their behaviour can be unpredictable. Hypergiants often vary in brightness as their outer layers expand and contract. They can lose vast amounts of mass in dramatic outbursts, briefly brightening and then fading again. Observing them is like watching a slow, drawn-out performance, where the main character is constantly changing shape and intensity. It is in this upper range of sizes that the stars we talked about earlier, like UY Scuti, begin to appear. These are the ones that stretch our sense of scale to its limits. Their diameters are so large that they are best described in terms of the orbits of planets rather than kilometres or miles. To help make this more concrete, some astronomers like to use a kind of mental map of the solar system. Imagine standing at the centre, where the Sun is now. Then imagine drawing circles outward to represent the orbits of the planets. Mercury is close in, Venus a bit farther, Earth farther still. Mars marks the edge of the inner solar system. Beyond that lies the asteroid belt, then the realm of the gas giants, with Jupiter and Saturn dominating the outer regions. A star the size of a typical red supergiant might reach out to somewhere between Mars and Jupiter. A star at the extreme end of the scale, like UY Scuti, could extend nearly to the orbit of Saturn. That means its diameter would be so wide that light itself would take hours to travel from one side to the other. At this point, the tour of stellar sizes begins to blur into something almost abstract. The numbers become so large that they are hard to hold on to in a practical way. Instead, the comparisons, planets, orbits, light travel times start to do the work of conveying scale. But it is also important to notice what happens when we move from small stars to large ones in terms of how they live their lives. The smallest stars are long-lived and stable. The largest stars are short-lived and volatile. There is a kind of trade-off between size and longevity. A red dwarf can quietly glow for far longer than the current age of the universe. A massive supergiant, on the other hand, may burn through its fuel in just a few million years. On cosmic timescales, that is a brief moment. These giant stars live fast and end dramatically, often exploding as supernovae and leaving behind dense remnants like neutron stars or black holes. So when we look at the largest stars, we are often looking at a phase that does not last very long. These stars are in a kind of late-life bloom, expanded and luminous, but already on a path toward a violent conclusion. This adds a layer of quiet tension to the image of these vast glowing spheres. They may appear calm and steady from our distant viewpoint, but inside their cores are running through a complex series of fusion reactions, building heavier and heavier elements. Each stage brings them closer to a point where the balance between gravity and pressure can no longer be maintained. In a way, the tour of stellar sizes is also a tour of stellar lifetimes. The small stars represent patience and persistence. The large stars represent intensity and impermanence. Another interesting aspect of this range is how it shapes what we can see from Earth. Small, dim stars are often invisible to the naked eye, even if they are relatively close. Large, luminous stars can be seen across vast distances, shining as bright points in the night sky even from thousands of light years away. Many of the familiar bright stars you might recognize by name: Betelgeuse in Orion, Antares in Scorpius, Aldebaran in Taurus, are red giants or supergiants. They stand out not because they are close, but because they are large and powerful enough to be seen across great stretches of space. This means that when you look up at the night sky, you're often seeing a biased sample of the stellar population. The small quiet stars vastly outnumber the big dramatic ones, but it is the big ones that catch your eye. So in a sense, our impression of the universe is shaped by its extremes. The largest and brightest stars leave the strongest visual imprint, even though they are relatively rare. As you move mentally along this scale, from red dwarfs to sun-like stars to giants and supergiants, you might notice how the concept of normal keeps shifting. What feels large at one point becomes modest a few steps later. What feels enormous eventually becomes just another point of reference on the way to something even bigger. This shifting perspective is one of the quiet lessons of astronomy. It teaches the mind to be flexible with scale, to accept that there is always something larger, something smaller, something farther, something closer. At the same time, it offers a kind of grounding. No matter how large a star becomes, it is still governed by the same basic principles. Gravity pulls, nuclear reactions push, energy flows from hot to cold. The same physics that operates in a small, steady red dwarf also operates in a vast, unstable hypergiant. That continuity can be comforting. It suggests that the universe, for all its size and complexity, is not chaotic in a random way. It follows patterns, it has rhythms. Even the biggest things grow and change in ways that can be understood, at least in part. As this calm tour of stellar sizes draws your attention upward and outward, you might find it easier to let your own thoughts drift a little more freely. The mind can wander from one glowing sphere to another, tracing imaginary paths across the galaxy, moving from quiet, dim stars to vast, luminous giants, and back again. And somewhere along that path, the idea of the largest star begins to feel less like a single destination, and more like a point on a broad, continuous landscape. It becomes part of a story about range, diversity, and the many ways matter and energy can organize themselves in the universe. Somewhere deep inside a quiet cloud of gas and dust, long before a star becomes anything that could be called a giant, its story begins in a far more modest way. A faint ripple passes through the cloud, perhaps triggered by a nearby explosion, a passing wave of pressure, or the slow pull of gravity itself. Over time, that ripple grows into a gentle collapse. Gas drifts inward. Dust gathers. The cloud becomes denser at its centre, and eventually the temperature and pressure rise high enough for the first sparks of nuclear fusion to ignite. A star is born. At this stage, no one looking at it from a distance would guess what it might become. It glows steadily, fusing hydrogen into helium in its core, balancing the inward pull of gravity with the outward push of energy. This is the long, stable phase of a star's life, known as the main sequence. Our own Sun has been in this stage for about 4.5 billion years, and is expected to remain there for several billion more. But stars, like all things, change. The art of swelling into a giant begins when that balance starts to shift. The key lies in the star's core, the region where nuclear fusion takes place. For most of a star's life, hydrogen atoms are fused together to form helium, releasing energy in the process. This energy flows outward and provides the pressure that keeps the star from collapsing under its own weight. But hydrogen is not an infinite resource. Over time, the core becomes richer in helium and poorer in hydrogen. When the hydrogen in the core runs low, the fusion process slows down. Less energy is produced. The outward pressure weakens. Gravity, which has been patiently pulling inward all along, begins to gain the upper hand. The core starts to contract. This contraction does not mean the whole star shrinks. In fact, something almost counterintuitive happens. As the core contracts, it heats up. The increased temperature ignites hydrogen fusion in a shell around the core rather than in the core itself. This shell of fusion produces a surge of energy that pushes the star's outer layers outward. The star begins to swell. Its surface moves farther and farther from the centre. As it expands, that surface cools, shifting the star's colour toward the red end of the spectrum. The once modest star becomes a red giant, larger, cooler on the outside, and far more luminous than it was before. For a star like the Sun, this transformation is dramatic but measured. The Sun will expand to many times its current size, likely engulfing the inner planets. Its outer layers will become tenuous and extended, forming a glowing envelope around a denser core. For more massive stars, the process follows the same basic pattern, but on a much grander scale. These stars begin their lives with far more material. Their cores burn hotter and faster. They move through the stages of their evolution more quickly. When they reach the point where hydrogen in the core is exhausted, the subsequent changes are more intense. The energy output from shell fusion is greater. The outward push on the outer layers is stronger. Instead of becoming simple red giants, these stars become red supergiants. A red supergiant is not just a bigger version of a red giant, it is a different kind of presence altogether. Its radius can grow to hundreds, or even thousands of times that of the Sun. Its outer atmosphere becomes a vast, gently glowing region of space, so large that it can encompass the orbits of multiple planets if placed in our solar system. Inside, the star's core is going through a complex sequence of nuclear reactions. After hydrogen, it begins fusing helium into heavier elements like carbon and oxygen. Later, it may fuse carbon into neon, neon into oxygen, oxygen into silicon, and silicon into iron. Each of these stages occurs in shells around the core, creating a layered structure somewhat like the layers of an onion. Each new fusion process releases energy, but each also brings the star closer to the end of its ability to generate that energy in a way that can support the star against gravity. All of this activity in the core contributes to the swelling of the outer layers. The star becomes a kind of balancing act on a colossal scale, with gravity pulling inward and multiple layers of fusion pushing outward in different ways. From the outside, what you see is a vast, red, luminous object glowing steadily in the dark. But beneath that calm appearance is a complex and dynamic interior, constantly adjusting to changes in temperature, pressure, and composition. One of the most striking features of red giants and supergiants is how diffuse their outer layers are. The density of gas near the surface can be extremely low, far lower than anything we experience on Earth. If you could somehow travel into the outer atmosphere of one of these stars, you would not encounter a sharp surface. You would drift through a thin, hot gas that gradually becomes denser as you move inward. This extended atmosphere is one of the reasons these stars can become so large in terms of radius, without necessarily being proportionally massive. Much of their size comes from this vast, puffy envelope rather than from a solid or dense core. The swelling process is not always smooth and steady. Many giant stars pulsate. Their outer layers expand and contract over time, driven by changes in the balance between energy output and gravity. These pulsations can cause the star's brightness to vary, sometimes quite noticeably. In some cases, the pulsations are regular, like a slow heartbeat. In others, they are more irregular, reflecting the complex interactions inside the star. By studying these variations, astronomers can learn about the star's internal structure and its stage of evolution. As these stars swell, they also begin to lose mass. The combination of low gravity at the surface and strong radiation pressure from the star's intense light can push material outward into space. This creates powerful stellar winds that carry gas and dust away from the star. Over time, this lost material can form vast shells or clouds around the star, glowing faintly as they are illuminated by its light. These surrounding structures can be beautiful, intricate, and, from a distance, almost ghostly. This mass loss plays a crucial role in shaping the star's future. It can reduce the star's mass significantly before it reaches the final stages of its life. It also enriches the surrounding space with heavy elements that were created inside the star. These elements become part of the raw material for future generations of stars and planets. So in a very real sense, the swelling of a giant star is also a process of giving back. This star that once formed from a cloud of gas and dust now returns enriched material to the galaxy, contributing to a cycle that spans billions of years. Among the most extreme examples of swelling stars are the hypergiants. These stars sit at the upper edge of what stellar physics allows. They're incredibly luminous and unstable, often losing mass at astonishing rates. A hypergiant might shed material so quickly that its surrounding nebula becomes thick and complex, shaped by the star's winds and eruptions. These stars can change their appearance over relatively short timescales, shifting in brightness and colour as their outer layers respond to internal changes. In some cases, a hypergiant may appear to grow and shrink dramatically over just a few years. This does not necessarily mean the star's core is changing that quickly, but rather that its outer atmosphere is responding to shifts in energy output and mass loss. Observing these stars can feel like watching a slow-motion drama unfold. Each new image or spectrum adds another piece to a story that is still being written. The idea of art in the phrase, "the art of swelling stars," fits in a curious way. Of course, there is no conscious design at work. The star is not choosing to become a giant. It is simply following the rules of physics, responding to changes in its internal fuel and energy balance. And yet the result is something that can feel almost expressive. The way a star expands, pulses, sheds material and glows can create patterns and structures that are visually striking and scientifically rich. From a human perspective, these changes can also serve as markers of time on a scale that feels both vast and intimate. The swelling of a star takes place over thousands or millions of years, far longer than any human life, and yet through careful observation, astronomers can trace these changes and reconstruct the story of a star's past and future. There is a certain quiet satisfaction in that. It is a way of connecting with a process that unfolds far beyond our own lifespan, using tools and ideas that allow us to see a little further than our natural senses would otherwise permit. As you think about these stars swelling and changing, it can be helpful to return briefly to the idea of scale. When a star becomes a red giant or supergiant, its volume increases enormously, but its mass does not necessarily increase at the same rate. In fact, it may be losing mass at the same time. This means that the star's density drops dramatically. The core remains dense and compact, but the outer layers become incredibly thin. The star becomes a kind of cosmic balloon, vast in size but light in structure. This combination of size and fragility is part of what makes these stars so fascinating. They dominate their regions of space visually and energetically, but they are also vulnerable to the very processes that sustain them. Their intense fusion reactions eventually produce iron in the core, and iron fusion does not release energy in the way lighter elements do. When that stage is reached, the delicate balance between pressure and gravity collapses. The star's core gives way. Gravity wins. The result is one of the most powerful events in the universe, a supernova, an explosion that can briefly outshine an entire galaxy and scatter the star's material across space. So the swelling of a giant star is not just a phase of growth, it is also a prelude. It is part of a larger arc that includes both creation and destruction, both expansion and collapse. For the larger stars, this arc plays out quickly. A star that swells into a supergiant or hypergiant may only remain in that state for a relatively short period before its life comes to a dramatic end. On cosmic timescales, it is a brief moment of immense presence. That fleeting quality adds a layer of poignancy to the idea of the larger stars. They are rare, not just because they are difficult to form, but because they do not last long in their most impressive state. When astronomers identify a star like UY Scuti or Canis Majoris as one of the largest known, they are catching it in a particular moment of its life, a moment that will not last forever. There is something quietly human in that. We often find beauty and meaning in moments that we know are temporary. A sunset, a season, a stage of life. The fact that it will pass can make it feel more precious. In the case of these giant stars, the passing happens on a scale far beyond our own experience, but the principle is similar. They're vast and luminous now, but they are also on a path toward transformation. You might notice how the idea of swelling stars creates a bridge between the smallest beginnings and the largest endings. A star forms from a thin cloud of gas. It grows, stabilizes, and then for some expands into something enormous. Finally, it gives back its material in a final, powerful release. This cycle is not just a story about stars. It is part of the story of everything made from atoms heavier than hydrogen and helium. The elements in our bodies, in the ground beneath us, and in the air we breathe were forged in the cores of stars and scattered by their deaths. So when you think about red giants and supergiants, you're also, in a very indirect way, thinking about your own origins. The larger stars play a role in shaping the chemical richness of the universe, seeding space with the building blocks of planets and life. Somewhere out there, scattered across the wide disk of our galaxy and beyond, are stars that do not simply shine. They announce themselves. They glow with a kind of presence that stands out even across thousands of light years, drawing the attention of telescopes and the quiet curiosity of the people who aim them. These are the colossal contenders, the stars that enter the conversation whenever someone asks about the largest known examples in the universe. It can be helpful to think of this not as a single champion standing alone at the top of a list, but as a small group of extraordinary objects, each with its own story, its own quirks, and its own place in the shifting landscape of astronomical measurement. The title of largest has moved among them over the years, not because the stars themselves are competing, but because our understanding of them continues to grow and refine. Let's begin with one of the most famous names to come up in this context, a star that for a long time held a kind of legendary status among both astronomers and sky enthusiasts. Its name is UY Canis Majoris. UY Canis Majoris is a red hypergiant located in the constellation Canis Major, the Great Dog, not far from Sirius, the brightest star in the night sky. Even though Sirius easily outshines it from our perspective, UY Canis Majoris is actually far more luminous. It simply lies much farther away. For many years, UY Canis Majoris was considered one of the largest stars known. Early estimates suggested that its radius might be well over 1,000 times that of the Sun, possibly even approaching 2,000 times. If placed at the centre of our solar system, it could have extended beyond the orbit of Jupiter, reaching into the outer realms where Saturn travels. What made Canis Majoris especially intriguing was not just its size, but its surroundings. observations revealed that it is enveloped in a vast complex nebula of gas and dust, material that the star itself has ejected over time. This nebula is full of arcs, knots and streams, suggesting a history of violent and uneven mass loss. Studying this structure gave astronomers a window into how massive stars shed their outer layers and how those layers interact with the surrounding space. It also added uncertainty to size measurements, because the star's light is filtered and scattered by its own debris, making it harder to pin down where the star's photosphere truly lies. As better distance measurements became available, particularly from space-based observatories, some of the earlier size estimates for VY Canis Majoris were revised downward. It is still an enormous star by any reasonable standard, but it may not be quite as extreme as once thought. Even so, it remains one of the most studied and visually striking examples of a swollen, unstable giant. Another name that often appears in discussions of colossal stars is Betelgeuse. This one is more familiar to many people, because it is one of the brightest and most easily recognizable stars in the night sky, forming the shoulder of the constellation Orion. Betelgeuse is a red supergiant, and it is relatively close to us on cosmic scales, just a few hundred light-years away. That proximity has allowed astronomers to study it in great detail, even resolving its surface with advanced imaging techniques. In terms of sheer size, Betelgeuse is not the largest star known, but it is large enough to give a vivid sense of what a supergiant is like. Its radius is estimated to be several hundred times that of the Sun. If it were placed at the centre of our solar system, it would extend beyond the orbit of Mars, possibly reaching into the asteroid belt. What makes Betelgeuse especially interesting is its variability. It changes in brightness over time, and in recent years it underwent a dramatic dimming event that captured public attention. For a while, people wondered whether it was about to explode as a supernova. While it has since brightened again, the episode highlighted how dynamic and unpredictable these large stars can be. They are not static spheres. Their surfaces shift, their outer layers move, and their light can vary in ways that reflect complex processes happening deep inside. Moving farther along the list of contenders, we come to a star that often sits near the top of modern rankings. This is UY Scuti, the one we touched on earlier. UY Scuti is a red supergiant located in the constellation Scutum. It is much farther away than Betelgeuse, and from our vantage point it appears as a faint star that requires a telescope to see. Its claim to fame comes from estimates of its radius, which placed among the largest known stars in terms of physical size. At its most generous estimates, UY Scuti's radius is around 1,700 times that of the Sun, though, as with all such measurements, there is a range of uncertainty. Even at the lower end of that range, it remains a truly enormous object. What makes UY Scuti particularly compelling is how it fits into our broader understanding of red supergiants. It has a relatively cool surface temperature, which contributes to its large size. Its luminosity is high, but not extreme compared to some other massive stars. This combination suggests that it is in a specific phase of its evolution, swollen but not yet at the very edge of stability. Another contender that often enters the conversation is a star known as Westerlund 1-26. This one is part of a dense star cluster called Westerlund 1, which lies in our galaxy and is known for containing a remarkable collection of massive, evolved stars. Westerlund 1-26 is a red supergiant with a size that may rival or even exceed that of UY Scuti, depending on the exact measurements and assumptions used. Being part of a cluster adds both opportunities and challenges for astronomers. On one hand, the cluster's distance can be estimated using multiple stars, which can improve accuracy. On the other hand, the dense environment can complicate observations, with light from nearby stars and interstellar material blending together. What stands out about Westerlund 1-26 is the environment it inhabits. The cluster is young by cosmic standards, meaning that many of its massive stars are still in relatively early or middle stages of their evolution. Seeing such a large red supergiant in this context helps astronomers test theories about how quickly and how far massive stars can swell. There are also stars that are less famous, known mostly by catalogue numbers that occasionally appear in lists of the largest candidates. Names like KY Cygni, NML Cygni, and others come up in scientific papers and discussions. NML Cygni, for example, is another red hypergiant with an extended atmosphere and a surrounding nebula shaped by its interaction with nearby stars and radiation. Its size estimates place it among the largest known, though, again, uncertainties in distance and atmospheric structure make precise ranking difficult. What all of these stars share is not just size, but a kind of complexity. They're often surrounded by clouds of material they have ejected. They show signs of strong winds, pulsations, and irregular behaviour. They sit at a point in stellar evolution where stability is hard to maintain. This complexity is part of what makes them so valuable to astronomers. By studying these extreme cases, scientists can learn about the limits of stellar physics. They can see how stars behave when they are pushed close to the boundaries of what gravity, pressure, and radiation can support. It is also worth noting that these colossal stars are not evenly distributed across the sky. They tend to form in regions where large amounts of gas and dust are available, often in spiral arms of galaxies or in dense star-forming clusters. These regions are busy, active places, filled with young stars, glowing nebulae, and the remnants of past supernovae. So when we look at a star like UY Scuti or Westerland 126, we are also glimpsing a broader environment, a neighbourhood shaped by repeated cycles of star birth and death. Another interesting aspect of these contenders is how their reputations change over time. A star might be identified as a potential record holder, only for later studies to revise its size downward. Another star might quietly move up the list as new data reveals that it is farther away or brighter than previously thought. This shifting landscape reflects the nature of astronomical research. It is not a race to crown a winner, but a gradual process of refining measurements and improving models. There is something gently reassuring about that. The universe does not demand that we get everything right on the first try. It allows us to learn, to correct, and to deepen our understanding over time. From a human perspective, these stars can also take on a kind of personality, even though they are just physical systems governed by natural laws. Betelgeuse becomes the familiar, nearby giant that we watch for signs of change. VY Canis Majoris becomes the dramatic, turbulent star wrapped in its own nebula. UY Scuti becomes the quiet, distant giant that stretches our sense of scale. These informal narratives are not part of the science itself, but they help people connect with objects that would otherwise be little more than points of light and lines of data. It is also interesting to think about how these stars appear from different vantage points in the universe. From Earth, they are distant and faint. From a hypothetical planet orbiting near one of them, the view would be overwhelming. Imagine standing on a world in the outer reaches of a system centred on a red supergiant. The star would fill a large portion of the sky, glowing softly but intensely, its surface marked by vast, slow-moving patterns of brighter and darker regions. The light would be redder and dimmer per unit area than the sun's, but because the star is so large, the overall effect would still be powerful. The idea of scale becomes immediate and visceral in that imagined scene. The star is not just a number, it is a presence. Of course, such a planet is unlikely to exist in reality, because the environments around these massive stars are often harsh and unstable. The intense radiation, strong winds, and eventual supernova explosions make long-term habitability improbable. Still, the mental exercise helps translate abstract measurements into something more tangible. As we move through this gallery of colossal contenders, it is worth remembering that all of these stars are, in a sense, snapshots. We see them as they were when their light began its journey toward us. For a star thousands of light years away, that light may have left the star before human civilization began. By the time we observe it, the star itself may have changed significantly, or even ended its life in a supernova. In that case, the largest star we are discussing might no longer exist in the form we imagine. This time delay adds another layer of quiet wonder to the process. The universe we see is always a little bit in the past. Our measurements, our rankings, and our stories are based on light that has travelled across both space and time. So when we talk about meeting these colossal contenders, we are really meeting their echoes, their recorded light, their messages sent long ago. There is something gentle and humbling about that. It reminds us that our connection to the universe is indirect, mediated by the slow, steady movement of light across vast distances. As you let that idea settle, you might notice how it softens the concept of a largest star. The stars themselves are not concerned with titles or comparisons. They exist, they change, and they eventually fade or transform. The labels and rankings are ours, tools we use to organise our understanding and satisfy our curiosity. Far out in the direction of a small and often overlooked constellation, one that does not carry the bold outlines of Orion, or the familiar curve of the Big Dipper, there is a faint point of light that quietly changed the way astronomers talk about size. This constellation is called Scutum, the Shield, and within its borders lies a star that for many became a kind of benchmark for what huge really means when the conversation turns to the universe. Its name is UY Scuti. From Earth, UY Scuti does not announce itself. You cannot step outside on a clear night, look up, and easily spot it with your eyes. It is too distant, too dim, and lost among countless other stars that appear brighter simply because they are closer to us. If you did not know where to point a telescope, you could sweep the sky for hours and never realize that one of the largest known stars in our galaxy was sitting quietly in your field of view. That contrast between its subtle appearance and its immense physical presence is part of what makes UY Scuti so fascinating. It is a reminder that in astronomy, what you see is often the smallest hint of what is really there. To begin understanding this star, it helps to place it in its cosmic neighbourhood. UY Scuti lies within the Milky Way galaxy, embedded in one of its spiral arms, in a region rich with gas, dust, and ongoing star formation. It is thousands of light years away from us, which means the light we see from it tonight began its journey long before modern telescopes existed. Long before most of the scientific language we use today had even been developed. When astronomers first began cataloguing stars like UY Scuti, they did so using relatively simple tools. They recorded positions, brightness, and colours. Over time, as spectroscopes and more powerful telescopes became available, they could start to classify stars by their temperatures and chemical compositions. UY Scuti stood out as a red star, which immediately placed it in the category of cool, evolved stars. Red does not mean cold in an everyday sense, of course. Its surface temperature is still thousands of degrees, but compared to hot blue stars that can reach tens of thousands of degrees, it is on the cooler end of the stellar spectrum. That cool surface temperature, combined with its brightness once distance was accounted for, hinted that UY Scuti must be very large. A star that shines brightly but is relatively cool must have a vast surface area to emit that much energy. As measurements improved, particularly with better estimates of its distance, the picture became clearer. UY Scuti was not just large, it was enormous. Estimates of its radius placed it at around 1,700 times the radius of the Sun, with some studies suggesting even larger values depending on the assumptions used. To put that into perspective, if you were to place UY Scuti where the Sun currently sits, its outer edge would extend far beyond the orbit of Jupiter and possibly approach the region of Saturn. Light itself would take hours to travel from one side of the star to the other. That is a time scale that begins to blur the line between an object and a region of space. And yet, despite this size, UY Scuti is not particularly massive compared to some other giant stars. Its mass is estimated to be perhaps 25 to 40 times that of the Sun, which is large, but not extreme by the standards of the most massive stars known. This highlights again the difference between mass and size. Much of UY Scuti's vastness comes from its extended, diffuse outer atmosphere rather than from a dense, heavy core. The star's structure is a layered one, like many red supergiants. Deep inside, at its core, nuclear fusion is still taking place, though not in the simple, steady way that occurs in a main sequence star like the Sun. UY Scuti has already burned through the hydrogen in its core. It has moved on to fusing heavier elements in shells around the centre. These fusion processes generate enormous amounts of energy, which push outward on the star's outer layers. That outward pressure is what keeps the star inflated to such an extraordinary size. At the same time, gravity is always pulling inward, trying to draw everything back toward the centre. The balance between these two forces is delicate, and in a star as large and evolved as UY Scuti, it is not perfectly stable. One of the signs of this instability is variability. UY Scuti is known to change in brightness over time. These changes are linked to pulsations in its outer layers, slow expansions and contractions that reflect shifts in the star's internal conditions. The timescales of these pulsations can be measured in months or years, which is slow by human standards, but relatively quick in the life of a star. By tracking these variations, astronomers can gain insight into the star's internal structure and the processes driving its evolution. Another striking feature of UY Scuti is the material that surrounds it. Like many red supergiants, it is losing mass through stellar winds. Gas and dust are being pushed away from the star, forming a kind of envelope around it. This envelope can absorb and scatter light, making it more difficult to measure the star's true brightness and size. It can also glow in infrared light, revealing structures that are invisible in the visible spectrum. Observations of UY Scuti in different wavelengths have shown that it is embedded in a complex environment shaped by its own activity. This environment is not static. It evolves as the star continues to shed material, and as that material interacts with radiation and nearby interstellar gas. From a measurement standpoint, this complexity is both a challenge and an opportunity. It complicates the task of defining where the star ends and where its surroundings begin. At the same time, it provides valuable information about how massive stars lose mass and how they influence the space around them. One of the reasons UY Scuti became such a prominent example in discussions of stellar size is timing. Its size estimates came into focus during a period when astronomers were refining their distance measurements across the galaxy. New data allowed for more accurate calculations of luminosity and radius, and UY Scuti emerged as a standout case. It became a reference point, a star that could be used to illustrate just how far the upper end of the size scale might extend. But as with other colossal stars, its status is not fixed. Some studies have suggested slightly smaller radii, while others have placed it firmly near the top of the list. The differences often come down to details like which distance estimate is used, how the star's temperature is measured, and how the effects of surrounding dust are corrected for. This means that UY Scuti is less a single, definitive answer, and more a symbol of the current state of our knowledge. It represents the kind of object that sits at the boundary of what we can measure with confidence. There is something quietly fitting about that. The largest things in the universe are often the hardest to pin down. They resist simple, clean numbers. Beyond the technical details, UY Scuti invites a more imaginative response as well. It is one thing to say, a star has a radius 1,700 times that of the Sun. It is another to try to picture what that means. Imagine standing on Earth and looking up at the Sun. It appears as a small, bright disk in the sky, easy to cover with a fingertip held at arm's length. Now imagine that disk expanding, growing larger and larger, until it fills a significant portion of the sky. On a hypothetical planet orbiting far out in the system of UY Scuti, the star would dominate the view. Its surface would not be a uniform, smooth glow. It would be marked by vast, slow-moving patterns, bright and dark regions caused by enormous convection cells in its atmosphere. These cells can be so large that each one could cover a region bigger than the entire sun. The light would be redder and softer in tone than the sun's, but because of the star's immense size, the overall brightness could still be overwhelming. Shadows would be deep and long. The sky would be painted with a warm, diffuse glow. Of course, such a planet is unlikely to exist in reality, at least not in a form that could support anything like life as we know it. The environment around a star like UY Scuti would be harsh, shaped by strong radiation, powerful winds, and the looming prospect of a supernova explosion. Still, the mental image serves a purpose. It helps translate an abstract number into a scene, something the mind can wander through. Another aspect of UY Scuti's story that often captures attention is its future. As a red supergiant, it is in a late stage of its life. It will not remain in this swollen state forever. At some point, the fusion processes in its core will reach a stage where iron begins to accumulate. Unlike lighter elements, iron fusion does not release energy. When that happens, the delicate balance between outward pressure and inward gravity will collapse. The core will give way. The outer layers will fall inward and then rebound in a catastrophic explosion. UY Scuti will end its life as a supernova, briefly becoming one of the brightest objects in its galaxy, visible across vast distances. That explosion will scatter the star's material into space, enriching the surrounding region with heavy elements. Over time, that material may become part of new stars, new planets, and perhaps, in some distant future, new forms of life. So the star that redefined huge will, in the end, become a source of new beginnings. This cyclical nature of stellar evolution adds a gentle sense of continuity to the story. Even the larger stars are not permanent fixtures. They are part of a flow of matter and energy that moves through different forms over cosmic timescales. There is also something quietly humbling about the fact that we know UY Scuti only through its light. We cannot visit it. We cannot observe it directly in any tactile sense. Everything we know about it comes from careful analysis of photons that have travelled across space for thousands of years. When you look at UY Scuti in a telescope, you're not seeing it as it is right now. You're seeing it as it was when that light left the star. If something dramatic were happening there at this very moment, we would not know about it for a long time. This time delay is part of the fabric of astronomy. It means that the universe we observe is always, in a sense, a record of the past. The largest stars we talk about are snapshots frozen in light, moments in long lives that we're catching only after they have already moved on. In the case of UY Scuti, this adds a layer of quiet mystery. It might still be there, glowing and swelling in its corner of the galaxy, or it might have already ended its life in a supernova, its light from that final event still on its way toward us. We do not know, and in a way that uncertainty is part of what makes the story feel alive. As UY Scuti gained attention in the astronomical community and beyond, it became a kind of shorthand for cosmic size. Articles, videos and classroom lessons began to use it as an example when talking about how big stars can get. This popular role does not diminish its scientific importance, but it does add a cultural layer to its identity. It becomes part of how people imagine the universe, a mental landmark in the landscape of extreme objects. At the same time, astronomers continue to study it not just as a curiosity, but as a data point in a larger effort to understand how massive stars evolve, lose mass, and ultimately die. Every observation, every spectrum, every measurement of its brightness and variability contributes to that broader picture. And that broader picture is still incomplete. There are likely other stars out there that rival or exceed UY Scuti in size, hidden in dense regions of the galaxy or in distant galaxies beyond our own. As telescopes become more powerful and surveys more comprehensive, new candidates may emerge. So UY Scuti's role as the star that redefined huge is both a recognition of what we have learned and a placeholder for what we have yet to discover. On one hand, there are numbers, measurements, and physical processes that describe the star in detail. On the other hand, there is the open horizon of the unknown, the possibility that even larger stars are waiting to be found. This balance is a recurring theme in astronomy. Each answer opens up new questions. Each discovery extends the boundary of what we can imagine. What would happen if a star like UY Scuti replaced our Sun? How would the solar system change? What would the sky look like? How would the rhythms of day and night be altered? It can be strangely grounding to take something so distant and abstract and gently place it right at the centre of what feels familiar. So for a moment, imagine a quiet shift in the universe. Not a violent explosion or a dramatic flash of light, but a slow, almost impossible exchange. The Sun, our steady, reliable star, fades away, and in its place, a star like UY Scuti settles into the same position at the heart of the solar system. There is no real way this could happen in reality, of course. Stars do not simply trade places. But as a thought experiment, it offers a way to bring the idea of cosmic scale down to a level the mind can walk through, step by step. The first thing that would change is not the light or the heat, but space itself, at least as we usually think of it. UY Scuti is so large that its outer layers would extend far beyond the orbits of the inner planets. In fact, the star's vast, swollen atmosphere would reach past the path that Jupiter takes around the Sun, and possibly close to where Saturn travels. That means that Mercury, Venus, Earth, Mars, and the entire asteroid belt would no longer exist as separate orbiting worlds. They would be inside the star, not inside in the sense of being plunged into a dense, fiery core, but inside a vast, diffuse envelope of hot gas. The star's outer layers are thin by everyday standards, more like an extremely hot, glowing fog than a solid surface. Still, for any planet that found itself there, the environment would be utterly destructive. The concept of an orbit would lose its meaning in this region. Instead of circling a bright, compact sun across empty space, Earth would be embedded in a slowly moving, turbulent atmosphere of stellar material. The familiar boundary between space and star would dissolve. Before even thinking about what would happen on the surface of Earth, it helps to consider the view from farther out. From the region where Saturn orbits today, the sky would be dominated by a colossal red disk. It would not appear as a small, bright circle like the Sun does now, but as a vast presence that fills a large fraction of the sky. The light would be softer in colour, tinged with deep reds and oranges, because UY Scuti's surface temperature is much cooler than the Sun's. But because the star is so large, the total amount of light reaching that distant orbit could still be intense. Shadows would stretch long and dark. The contrast between light and dark might feel less sharp, because the star's enormous size would mean that light comes from a wide area rather than a single, concentrated point. The sky might take on a kind of constant, glowing twilight, rather than a crisp, directional daylight. Closer in the region where Jupiter orbits now, the experience would be even more overwhelming. The star would not just dominate the sky, it would define it. The concept of a night sky would be hard to maintain when the star's glowing surface wraps around so much of your field of view. Of course, this is all hypothetical. A planet could not realistically survive in such an environment. The radiation, heat, and stellar winds would strip away atmospheres and break down surfaces, but imagining the scene helps translate the star's size into something more experiential. Now, if we gently return our attention to Earth's original position, things become even more dramatic. Earth's orbit lies well within the volume that UY Scuti's outer layers would occupy. That means that Earth would be immersed in the star's extended atmosphere. The temperature would rise far beyond anything life could tolerate. The oceans would boil away, the atmosphere would be stripped and mixed into the star's outer layers. The planet itself would eventually be broken down, its material becoming part of the star's swirling envelope. But before that final merging, there would be a kind of transition zone. The star's outer atmosphere is not uniform. It is dynamic, full of slow-moving currents, rising and falling regions of gas, and vast convection cells that carry heat from the interior toward the surface. If Earth were placed within this environment, it would experience something like a continuous global storm. Not wind in the way we understand it, but large-scale flows of hot ionized gas, moving in patterns shaped by the star's internal energy. The familiar cycles of day and night would vanish. There would be no sunrise or sunset. Instead, there would be a constant glowing presence all around, a kind of endless reddish light filtering through layers of stellar material. Gravity, too, would feel different. UY Scuti's mass is greater than the Sun's, though not hundreds of times greater. Still, the gravitational field at a given distance from the centre would be stronger. Orbits in the outer solar system would shift. The paths of surviving planets and objects would change, reshaped by the new central mass. The Kuiper belt and the distant Oort cloud, the far-flung regions of icy debris at the edge of the solar system, would feel the tug of this new star. Comets might be drawn inward or flung outward, their long, slow journeys altered by the changed gravitational landscape. It is interesting to think about how the solar system as a whole would respond. The inner regions would be consumed. The middle regions would be transformed. The outer regions would adapt to a new balance of forces. In this imagined scenario, the largest star does not just replace the Sun, it redefines the entire structure of the system. Another layer to consider is time. UY Scuti, like other red supergiants, is in a late stage of its life. It is not a stable, long-term presence like the Sun. It is moving toward an ending that will be sudden and powerful. So in this thought experiment, even if a distant observer were watching from far beyond the star's reach, they would be witnessing a system that is living on borrowed time. At some point, perhaps in tens or hundreds of thousands of years, the star would reach the end of its ability to support itself. The core would collapse. The outer layers would be blasted outward in a supernova explosion. That explosion would send a wave of energy and material racing across the solar system's former territory. Anything that remained would be bathed in intense radiation and shock waves. The debris of the star would spread out, forming a glowing remnant that could persist for thousands of years. From a safe distance, the scene would be spectacular. From anywhere nearby, it would be catastrophic. But stepping back from the dramatic ending, it is also worth thinking about the quieter, more subtle changes that would come first. For example, the way light would behave. Because UY Scuti's surface is so large, different parts of it would be at slightly different distances from any given point in the system. Light from one side of the star would take longer to arrive than light from the other. The difference might be measured in minutes or even hours. This means that the star would never appear as a perfectly synchronized object. Changes on its surface would be seen at slightly different times, creating a kind of built-in delay across its face. The surface itself would be a shifting landscape. Enormous convection cells, each one larger than the Sun, would rise and fall over months or years. Bright regions would appear and fade. Darker patches would drift across the glowing disk. If you could watch the star from a stable vantage point, you would see it slowly, almost imperceptibly, changing shape and brightness over time. This kind of view helps highlight the difference between our Sun and a red supergiant. The Sun is dynamic too, with sunspots, flares and cycles of activity, but its overall shape and brightness remain fairly consistent on human timescales. A star like UY Scuti is more restless, more visibly in flux. Another subtle effect would be the way sound and vibration might travel through the star's extended atmosphere. In reality, space is mostly silent, because sound requires a medium to travel. But within the star's outer layers, there is plenty of material. If a planet or object were somehow embedded there, It would be surrounded by a medium that could carry pressure waves. The star's pulsations and internal movements could, in theory, be felt as slow, deep vibrations, a kind of stellar hum. This is a speculative and poetic way to think about it, but it underscores the idea that being inside a star's atmosphere would be a very different experience from orbiting in empty space. There is also the question of scale when it comes to human-made structures and distances. The entire journey from Earth to the Moon, which feels so vast in the context of space travel, would be insignificant compared to the size of UY Scuti. The distance light travels from one side of the star to the other would dwarf the distances between planets in the inner solar system. This can make our usual reference points feel small in a way that is not discouraging, but clarifying. It shows how much our sense of scale is shaped by what we are used to. Another angle to consider is how this change would look from far outside the solar system. From a distant star, the system would appear as a large red supergiant surrounded by a cloud of debris and altered orbits. The familiar pattern of a yellow star with a set of stable planets would be gone. Over time, as the star shed mass and eventually exploded, the region would become a complex, expanding nebula, glowing in different colours as various elements were excited by radiation. Eventually that material would mix back into the interstellar medium, becoming part of the raw material for new stars and planets elsewhere in the galaxy. So in this imagined swap, the solar system does not just end. It transforms into something else, something that contributes to the next generation of cosmic structures. This brings a kind of cyclical feeling to the thought experiment. Even in a scenario that seems destructive from a human perspective, there is also creation happening on a different scale and time scale. Another way to approach this idea is to think less about physical destruction and more about the change in rhythm. Our current sun provides a steady, predictable pattern. Days and nights follow a regular cycle. Seasons shift gradually. The energy input to the Earth system is relatively stable. A star like UY Scuti would not offer that kind of regularity. Its brightness varies. Its outer layers move and pulse. Its energy output can change over time. If a planet could somehow exist at a safe distance, it would experience a sky that is less predictable. Light levels might rise and fall over months or years. The colour of the star might shift subtly. The environment would feel less steady, more like a long, slow wave than a fixed backdrop. This highlights another difference between small, stable stars and large, evolved ones. Stability and longevity often go together. The larger stars trade that stability for size and intensity. Thinking about that trade-off can lead back to a more personal reflection. In many areas of life, growth and intensity come with a kind of instability. Things that expand quickly or reach extreme states often do not stay there for long. Things that change slowly tend to last. The universe, in this sense, mirrors patterns we recognize in other contexts, just on a much larger canvas. As this thought experiment unfolds, it can also be helpful to remember that it is just that, a way of exploring an idea rather than a prediction or a possibility. The sun will not be replaced by a red supergiant. Our solar system has its own long, slow future, shaped by the sun's own evolution. But by imagining such a replacement, we get a chance to feel, rather than just calculate, what largest star really means. We get to move from numbers and diagrams to scenes and sensations, from abstract comparisons to a kind of mental landscape, and in doing so, the idea of UY Scuti or any other colossal star becomes more than a data point. It becomes a presence, something that can be pictured, even if only in a soft, drifting way. As this imagined sky fades back into the familiar one, with our smaller, steadier sun at its centre, the contrast can feel gentle rather than jarring. The sun's modest size, by cosmic standards, becomes part of what makes it such a reliable companion for life on Earth. The larger stars are impressive and awe-inspiring, but they are also fleeting and volatile. Our star is not a record holder, but it is a steady one. That thought can linger quietly, shifting attention from this imagined replacement back toward the broader question of why such enormous stars exist at all. How does a star manage to grow to that size in the first place? What conditions in the universe allow matter to gather, ignite, and swell into something that can stretch across planetary orbits? Long before a massive star ever glows brightly enough to earn a name in a catalogue or a place in a list of cosmic giants, its story begins in a part of the universe that is almost the opposite of what you might expect. Not in light, not in heat, not in brilliance, but in darkness. Quiet, cold, drifting darkness, where vast clouds of gas and dust hang suspended in the spaces between the stars, barely noticeable against the black backdrop of space. These clouds are known as molecular clouds, and they are some of the largest structures in a galaxy. They can stretch across dozens or even hundreds of light years. From a distance, they look like shadowy patches blotting out the stars behind them. Inside, the temperature is low, often just a few degrees above absolute zero. The gas is thin, far thinner than any vacuum humans can create on Earth, yet when spread across such enormous volumes, it contains enough material to form thousands or even millions of stars. It is here, in these quiet, cold regions, that the seeds of the most massive stars are planted. For a long time, nothing seems to happen. The cloud drifts, shaped by gentle motions, by the slow pull of gravity, by the distant influence of supernova explosions or passing spiral arms. Then, at some point, a small imbalance begins to grow. A region of the cloud becomes slightly denser than its surroundings. That small difference is enough. Gravity begins to pull more material into that denser patch. As more gas and dust gather, the gravitational pull grows stronger, which draws in even more material. The process feeds on itself. The region starts to collapse inward, very slowly at first, then faster as it becomes heavier and more compact. This is how all stars begin, whether they will one day become a quiet red dwarf or a colossal supergiant. But the path toward becoming truly massive starts with having access to a lot of material and having it quickly. In many parts of a molecular cloud, the collapsing regions remain relatively small. They form stars not much larger than the Sun, or even smaller. But in certain environments, especially in the densest, most active parts of a cloud, the conditions allow a forming star to gather enormous amounts of gas before anything can stop the process. These environments are often found in giant star-forming regions, places where clusters of stars are born together. You might picture these regions as cosmic nurseries, crowded and busy, with many stars forming at once, each one competing in a sense for the same pool of raw material. In such a crowded environment, the future massive stars are the ones that manage to grow quickly and dominate their surroundings. As a collapsing region gathers mass, it begins to heat up at its centre. The gravitational energy of the falling material is converted into heat, and a protostar forms. At this stage, the object is not yet a true star. It is more like a glowing embryo, wrapped in a thick cocoon of gas and dust. This cocoon hides the forming star from view in visible light. Astronomers often rely on infrared and radio observations to peer into these regions, because those wavelengths can pass through the dust more easily. Inside the cocoon, the protostar continues to grow. Gas spirals inward, often forming a rotating disk around the central object. This disk feeds material onto the protostar, allowing it to increase in mass. For a star that will eventually become very massive, this feeding process is intense. Material falls in at a rapid rate. The protostar's mass climbs quickly, and its internal temperature rises. Here, something interesting happens. As the protostar grows more massive, it also becomes more luminous. Even before nuclear fusion fully ignites in its core, it begins to emit significant amounts of radiation. that radiation pushes outward on the surrounding gas and dust. In theory, this outward pressure should act as a brake, slowing or even stopping the flow of material onto the star. For a long time, this created a puzzle for astronomers. How can a star grow to be dozens or even hundreds of times more massive than the Sun if its own light should push away the very material it needs to keep growing? The answer appears to lie in geometry and motion. The material falling onto a forming massive star does not come in evenly from all directions. Instead, it tends to flow along the disk and in dense streams. The radiation, on the other hand, escapes more easily along the poles of the system, where there is less material in the way. This creates a kind of cosmic balancing act. The star's light pushes outward, but the incoming gas finds paths where it can still fall inward. In some cases, the forming star also launches powerful jets along its poles, which can carve out channels in the surrounding cloud, shaping the environment and allowing material to continue feeding the star from the sides. So the birth of a massive star is not a quiet, gentle process. It is dynamic, energetic, and in a way, a little messy. As the protostar's core grows hotter and denser, it eventually reaches the point where hydrogen fusion ignites. This marks the moment when the object becomes a true star. For a massive star, this moment can come surprisingly early in its growth. Fusion can begin while the star is still gathering material from its surroundings. That means the star is already shining brightly and pushing outward with radiation even as it continues to gain mass. This early ignition sets massive stars apart from their smaller cousins. A star like the Sun spends a long time in a relatively quiet, stable formation phase before fusion begins. A massive star, by contrast, becomes active and influential almost as soon as it is born. Once fusion is underway, the star's influence on its environment increases dramatically. Its intense light ionizes the surrounding gas, heating it and causing it to expand. This can trigger the formation of new stars in some regions by compressing nearby gas, while in other regions it can blow material away, shutting down further star formation. In this way, massive stars become architects of their neighbourhoods. They shape the structure of the molecular cloud they were born from, carving out cavities, lighting up nebulae, and setting the stage for the next generation of stars. But what determines whether a massive star will one day become merely large, or truly enormous, like the red supergiants and hypergiants we have been talking about? Part of the answer lies in how much mass the star manages to gather during its formation. The more mass it starts with, the more dramatic its later evolution will be. A star that forms with 10 times the mass of the Sun will follow a different path than one that forms with 30 or 40 times the Sun's mass. The environment matters as well. The density of the molecular cloud, the presence of nearby forming stars, the turbulence in the gas, and even the chemical composition of the region can all influence how much material a star can accumulate. Stars forming in clusters can also interact with one another. In very dense clusters, stars can pass close enough for their gravitational fields to disturb each other's disks or envelopes. In some extreme cases, forming stars may even merge, combining their mass into a single, larger object. This kind of stellar merging is thought to be rare, but in the most crowded and massive clusters, it could play a role in creating the heaviest stars known. Once a massive star has finished gathering material and settles into its main sequence phase, its future size is already, in a sense, written into its initial conditions. The amount of fuel it has, the pressure in its core, and the way energy flows through its layers will determine how it evolves. As it burns through its hydrogen, then its helium, and then heavier elements, the internal balance shifts. Each new stage of fusion changes the star's structure, often leading to expansion. The stars that begin their lives with the greatest mass are the ones that have the potential to swell into the largest red supergiants and hypergiants later on. Their powerful fusion reactions create the conditions for their outer layers to be pushed far from the core, forming those vast, diffuse envelopes that define the upper end of the size scale. There is something quietly poetic about this connection between beginnings and endings. The larger stars owe their immense final size to the richness of their birth environment. The more material they gather at the start, the more dramatic their later expansion can be. Another aspect worth noticing is the role of time. Massive stars form quickly by cosmic standards. While a small star might take tens of millions of years to fully form, a massive star can complete much of its growth in just a few 100,000 years. This rapid pace is both a cause and a consequence of their intense nature. The fast accumulation of mass leads to high internal temperatures and pressures, which in turn drive powerful radiation and winds. So from the very beginning, massive stars are in a hurry. They burn brightly, live briefly, and leave strong imprints on their surroundings. It is also interesting to consider the broader galactic context. Massive stars are more likely to form in certain parts of a galaxy, such as spiral arms, where gas and dust are concentrated and star formation is active. In more quiet, sparse regions, the conditions may favour the formation of smaller, longer-lived stars instead. This means that the larger stars are not just individual objects. They are part of a pattern, tied to the structure and evolution of their host galaxy. Looking even farther out in other galaxies, astronomers find regions of intense star formation known as starburst regions. These areas can produce large numbers of massive stars in a relatively short period of time. In such environments, the chances of forming truly enormous stars may be higher. So when we talk about the birth of the larger stars, we are also talking about the life of galaxies, about how gas flows, how spiral arms move, and how energy and matter cycle through cosmic structures. From a human perspective, all of this happens on timescales and distances that are hard to grasp. The cloud that gives rise to a massive star may exist for millions of years. The star itself may live for only a few million more before ending its life in a supernova. And yet, the light from that star can travel for thousands or millions of years to reach us, allowing us to study a moment in its life long after that moment has passed. There is a kind of gentle irony in that. The larger stars are born quickly and live briefly, but their stories can echo across the universe for far longer than their physical existence. As you think about these beginnings, about cold clouds slowly collapsing and bright protostars carving out their place in the dark, it can feel like a slow unfolding rather than a single dramatic event. Even the most massive stars do not appear all at once. They emerge through a sequence of stages, each one building on the last. That gradual process mirrors, in a way, how we come to understand them. Observations accumulate, models improve, ideas are refined. The picture becomes clearer, but it is always open to adjustment. So when we look at a star like UY Scuti or any of the other colossal giants, we are not just seeing an endpoint, we are seeing the result of a long chain of events that began in a quiet, cold corner of a molecular cloud, with a small imbalance in density that grew, slowly and steadily, into something that now stretches across a region of space larger than our entire planetary system. From here, it feels natural to follow that chain forward in time, to ask what happens after these massive stars reach their enormous size. How long do they stay in that swollen state? What processes drive them toward their final moments? And why? For all their size and power, their lives are so much shorter than those of their smaller, steadier cousins. At first glance, it feels almost backwards. When you think about something that is big, solid, and powerful, it is easy to assume it will last a long time. Mountains seem more permanent than pebbles. Old trees feel more enduring than young shoots. So when people hear about stars that are dozens of times more massive than the Sun and thousands of times larger in size, it can feel natural to imagine them as ancient, long-lasting fixtures of the universe. But the reality is the opposite. The biggest stars live the shortest lives. This idea can take a moment to settle in, because it runs against everyday experience. In the cosmic sense, being large and powerful comes with a kind of urgency. These stars burn through their fuel at an astonishing rate, and their immense size is part of what drives that rapid pace. To understand why, it helps to return to the core of a star, where everything that matters most is happening, even though it is hidden from view. Inside any star, the basic process is the same. Gravity pulls inward, trying to compress the star into a smaller and smaller space. In response, the star's core heats up. When the temperature and pressure become high enough, nuclear fusion begins. Hydrogen atoms fuse into helium, releasing energy. That energy pushes outward, creating pressure that balances gravity. For a star like the Sun, this balance is steady and gentle. The Sun's core temperature is around 15 million degrees Celsius. That is an enormous number by human standards, but in the context of stars it is relatively moderate. The rate of fusion in the Sun's core is slow enough that it can continue shining in much the same way for about 10 billion years. Now consider a star that is 10, 20 or even 40 times more massive than the Sun. Its gravity is much stronger. That stronger gravity compresses the core more tightly, raising the temperature and pressure to much higher levels. At those higher temperatures, nuclear fusion happens much more quickly. The reactions speed up. Hydrogen is consumed at a far greater rate. The star becomes intensely luminous, pouring out energy at a pace that dwarfs that of smaller stars. So even though a massive star starts its life with much more fuel, it uses that fuel far less efficiently. It is like a powerful engine that burns through a full tank in a short burst of speed rather than cruising slowly over a long distance. This relationship between mass, temperature and fusion rate is one of the key reasons why the biggest stars live fast and die young. There is a simple way to think about it. A star that is 10 times as massive as the Sun is not just 10 times as bright. It can be thousands or even tens of thousands of times as luminous. That means it is using up its fuel at a vastly accelerated pace. This is not a linear relationship. As mass increases, the rate of energy production increases much more steeply. A small increase in mass can lead to a very large increase in brightness and energy output. So while a red dwarf star might sip its hydrogen slowly and steadily for hundreds of billions of years, a massive star gulps it down in just a few million. Once the hydrogen in the core runs low, the story does not end. The star moves on to new stages of fusion, just as we discussed earlier. The core contracts and heats up, and helium fusion begins, creating carbon and oxygen. Then, in the most massive stars, the process continues. Carbon fuses into heavier elements. Neon, oxygen, and silicon fusion follow. Each of these stages happens faster than the one before. Hydrogen fusion can last millions of years. Helium fusion might last hundreds of thousands. Carbon fusion can be over in a matter of centuries. Silicon fusion, the final stage before collapse, can take just days. This accelerating timeline is another reason the lives of massive stars feel so brief. The closer they get to the end, the faster things happen. And at the very centre of all this activity is a kind of countdown. The star is building heavier and heavier elements in its core. Eventually it produces iron. Iron is a turning point. Unlike the fusion of lighter elements, which releases energy, the fusion of iron does not. It actually consumes energy. When the core becomes dominated by iron, the star loses its main source of outward pressure. Gravity, which has been held at bay for millions of years, suddenly has nothing to oppose it. The core collapses. This collapse happens in a fraction of a second. The core falls inward, becoming incredibly dense. In many cases it rebounds, sending a shock wave outward that tears through the star's outer layers. The result is a supernova, one of the most powerful explosions in the universe. So the life of a massive star is shaped by a kind of inevitability. From the moment it is born with a large amount of mass, its fate is set on a fast track. Its core will burn hot. Its fuel will be consumed quickly. Its ending will be dramatic. But why, you might wonder, does having more mass lead to such inefficiency? Why can't a massive star simply burn its fuel slowly, like a red dwarf, and last longer? The answer lies in the balance of forces inside the star. Gravity scales with mass. The more mass a star has, the stronger the inward pull. To counter that stronger pull, the star needs a stronger outward push, which means more energy production. That energy comes from fusion, and fusion depends on temperature, so the star's core becomes hotter, which makes fusion happen faster. There is no easy way for the star to turn down this process. The laws of physics set the relationship between gravity, temperature and pressure. In a sense, the star is trapped by its own size. Its mass demands a certain level of energy output to maintain balance, and that level of output requires a high rate of fuel consumption. There is also another factor at play, and that is mass loss. The biggest stars do not just burn fuel, they also lose material over time. Their intense radiation and strong stellar winds push gas away from the star's surface. In some cases, this mass loss can be dramatic, with the star shedding large amounts of material into the surrounding space. This process can reduce the star's mass significantly over its lifetime. It can even change the star's evolutionary path, affecting how it will eventually end its life. But even as mass is lost, the core remains hot and active. The overall timeline is not extended in any meaningful way. The star is still racing through its stages of fusion. Another way to look at this is to compare the lives of stars of different sizes side by side. A red dwarf, the smallest type of star, might have a mass just a fraction of the Sun's. Its core temperature is relatively low. Fusion happens slowly. The star glows dimly. It uses its hydrogen so efficiently that it can continue shining for trillions of years. A star like the Sun sits in the middle. It is more massive and more luminous than a red dwarf. It will burn for about 10 billion years. A massive star, perhaps 20 times the mass of the Sun, will shine intensely and live for only a few million years. So as you move up the scale of stellar mass, the lifespan drops dramatically. This relationship can feel almost poetic in its simplicity. The stars that shine the brightest, that dominate their regions of space, that grow into the largest and most impressive forms, are also the ones that pass through their lives the fastest. There is a kind of trade-off between intensity and endurance. Another aspect of this short lifespan is the effect massive stars have on their surroundings. From early in their lives, they produce strong ultraviolet radiation that ionizes the gas around them, creating glowing regions known as H2 regions. Their stellar winds carve out cavities in molecular clouds. These actions can both trigger and suppress the formation of other stars nearby. In some cases, the pressure from a massive star's radiation compresses nearby gas, leading to the birth of new stars. In other cases, it blows material away, preventing further star formation. So even while they live, massive stars are shaping their environments in ways that reflect their intense, fast-paced nature. Their eventual supernova explosions take this influence to an even higher level. The explosion sends shock waves through surrounding space, compressing gas, heating it, and seeding it with heavy elements. This can kickstart new rounds of star formation in nearby regions. So although massive stars live short lives, their impact can be long-lasting. They act as catalysts in the ongoing cycle of matter in the galaxy. From a broader perspective, this rapid life cycle plays a key role in the chemical evolution of the universe. The heavy elements that make up planets, oceans and living organisms are forged in the cores of massive stars and spread through space by their deaths. If all stars lived long, quiet lives like red dwarfs, the universe would be a much simpler, more chemically limited place. The short, intense lives of massive stars are what enrich the cosmos and make complexity possible. So their brevity is not just a quirk, it is part of what makes the universe the way it is. There's also something quietly reflective in the idea that the largest stars, for all their power and size, are among the most fleeting. They blaze into existence, dominate their surroundings, and then disappear in a brilliant finale, leaving behind traces that persist long after the star itself is gone. This can echo in human ways of thinking, even though the scales are so different. there is a familiar pattern in which things that burn the brightest, that reach the highest intensity, often do not last as long as things that move more slowly and steadily. Of course, stars are not making choices, they are following physical laws, but the pattern can still feel meaningful when you step back and look at it as part of a larger story. Another layer to this is the way we observe these stars. Because they live such short lives, they are relatively rare. At any given time, only a small fraction of the stars in a galaxy are in the massive supergiant phase. That rarity adds to their mystique. When we see a red supergiant or hypergiant, we are catching a star in a brief, special moment of its life. It also means that our understanding of these stars is based on a limited sample. We have to piece together their life stories from observations of different stars at different stages, rather than watching a single star evolve from birth to death. In a sense, astronomers are reconstructing a long, complex narrative from a series of snapshots. This makes the study of massive stars both challenging and rewarding. Each new observation can fill in a missing piece, refine a model, or reveal a new twist in the story. There is also the matter of perspective. From the star's point of view, if such a thing could be said to exist, its life might feel long. Millions of years is an immense span of time compared to human history. Entire species rise and fall on Earth in a fraction of that period. So while we describe massive stars as living short lives, that is only in comparison to other stars. In absolute terms, their existence still stretches far beyond anything we experience directly. This duality, short-lived on cosmic scales, long-lived on human ones, can be a gentle reminder of how relative our sense of time is. What feels fleeting in one context can feel endless in another. As you sit with this idea, you might find it interesting to think about how many massive stars have already lived and died since the universe began. Each one has left behind a cloud of enriched material. Over billions of years, those clouds have mixed and recycled, becoming part of new stars, new planets, and eventually new forms of life. So even though individual massive stars are brief, their collective legacy is vast and enduring. This brings a quiet sense of continuity to the story. The largest stars may vanish quickly, but what they create and contribute continues to flow forward in time. When a massive star reaches the point where its fuel is nearly spent and its vast, swollen form can no longer hold itself up, the change does not come all at once, at least not from the star's own point of view. From the outside, we often talk about supernovae as sudden, violent events, bright flashes that briefly outshine entire galaxies. But before that moment of brilliance, there is a long, quiet, and deeply intricate process unfolding inside the star, one that can take thousands or even hundreds of thousands of years. This slow approach toward a dramatic fate begins deep in the star's core, in a region we can never see directly, but can only understand through models, equations, and the faint clues carried by light. Inside a red supergiant or hypergiant, the core has already moved beyond the simple fusion of hydrogen into helium. It has passed through stage after stage, building heavier and heavier elements in a layered structure. Each layer is like a shell around the core, fusing a different element, producing energy, and contributing to the delicate balance that keeps the star from collapsing. Closest to the centre, the heaviest elements are found. Outside that, lighter elements occupy their own layers. It is a complex, dynamic system, with energy flowing outward and material slowly shifting under the competing influences of gravity and pressure. As long as the star can continue to fuse elements that release energy, this structure can be maintained. The outward pressure from fusion counteracts the inward pull of gravity, and the star, no matter how large and unstable it may seem from the outside, remains standing. But the list of elements that can be fused in this way is limited. Each step up the periodic table brings the star closer to a point where fusion no longer helps. When the core begins to fuse silicon into iron, the end is approaching. This stage is brief, sometimes lasting only days or weeks. iron sits at a special place in nuclear physics. Fusing iron does not release energy. Instead, it consumes it. So when the core becomes dominated by iron, the star's main source of outward pressure disappears. Gravity, which has been held back for millions of years, suddenly has nothing opposing it. The collapse that follows is astonishingly fast. The core falls inward at a significant fraction of the speed of light. In less than a second, it shrinks from a region thousands of kilometers across to something much smaller and far denser. What happens next depends on the mass of the core. In some cases, the collapse is halted when the core becomes so dense that the particles inside it can no longer be squeezed any closer together. The core stiffens, rebounds, and sends a powerful shock wave outward. This shock wave races through the star's outer layers, heating them, accelerating them, and eventually blasting them into space. The result is a supernova explosion. From a distance, this explosion can be breathtaking. For a brief period, the dying star can shine brighter than all the other stars in its galaxy combined. The light can be seen across millions of light years. But while the flash itself is brief, the effects are anything but. The outer layers of the star are flung outward at tremendous speeds, carrying with them the elements that were forged inside the star during its life. These include not just hydrogen and helium, but heavier elements like carbon, oxygen, silicon and iron, as well as even heavier ones created in the chaos of the explosion itself. As this material expands into space, it forms a supernova remnant, a vast glowing cloud that can persist for thousands, or even tens of thousands of years. These remnants are some of the most beautiful and complex structures in the universe, filled with filaments, knots, and shock fronts, glowing in different colours depending on which elements are present and how they are being excited by radiation and collisions. So even after the star itself is gone, its presence is still felt, written across a wide region of space in light and motion. At the centre of this expanding cloud, something remains. The collapsed core does not simply vanish. It becomes one of the most extreme objects in the universe. If the core is not too massive, it becomes a neutron star. This is an object about the size of a city, but with more mass than the sun. The matter inside it is so dense that a teaspoon of it would weigh billions of tons. Neutron stars can spin rapidly, emit beams of radiation, and produce some of the most precise natural clocks known, in the form of pulsars. If the core is more massive, the collapse continues beyond the point where even neutron pressure can stop it. In that case, a black hole forms, a region of space where gravity is so strong that not even light can escape. So the fate of a giant star can be to leave behind either a small, incredibly dense remnant or a point of darkness that warps the space around it. Both outcomes are, in their own way, as extreme as the star that came before. But there is another layer to this story, one that unfolds more slowly and quietly in the space around the star and far beyond. The material ejected in a supernova does not simply drift away and disappear. Over time, it mixes with the surrounding interstellar medium, the thin gas and dust that fill the spaces between stars. This enriched material changes the chemical makeup of that medium. It adds heavier elements that were not present in large amounts before. These elements become part of future generations of stars and planets. When new molecular clouds form and begin to collapse to create new stars, they incorporate this recycled material. So a star born billions of years after a supernova may contain atoms that were once part of a massive star that lived and died long ago. This is how the universe becomes more complex over time. The earliest stars formed from almost pure hydrogen and helium. Later stars formed from material that included heavier elements, making it possible for rocky planets, oceans, and life to exist. So the dramatic fate of the universe's giants is not just an ending, it is also a beginning. This idea can feel comforting when you step back and look at it in a broader context. Even the most powerful and short-lived objects in the universe are part of a cycle that creates new possibilities. But the path toward that ending is not always a smooth single step. For some massive stars, especially the largest and most unstable ones, the final stages can involve a series of dramatic outbursts before the ultimate collapse. These stars may experience episodes where they shed large amounts of material in sudden eruptions. These eruptions can create multiple shells of gas around the star, each one marking a previous phase of mass loss. When the star eventually explodes as a supernova, the shock wave can collide with these shells, creating additional bursts of light and complex structures in the resulting remnant. In some cases, these interactions produce what are known as superluminous supernovae, events that are even brighter than typical supernova. These rare explosions are still an active area of research, and they may be linked to the most massive and unstable stars. There are also stars that may avoid a classic supernova altogether. Some very massive stars might collapse directly into a black hole, with little or no visible explosion. From the outside, such an event could look like a star that simply fades away. This possibility adds another layer of mystery to the fate of the larger stars. Not all endings are loud and bright. Some may be quiet and subtle, detectable only through careful observation of changes in a star's surroundings or through the detection of gravitational waves. Gravitational waves, ripples in the fabric of space itself, are another way these dramatic events leave their mark. When massive stars collapse, or when their remnants merge, they can produce waves that travel across the universe, carrying information about the most extreme conditions imaginable. These waves can pass through Earth, gently stretching and squeezing space by tiny amounts that require incredibly sensitive instruments to detect. In this way, the death of a giant star can be felt quite literally across vast distances. This adds yet another dimension to the idea of a star's fate. It is not just a visual spectacle, it is a physical event that can influence space itself. From a more human perspective, it is interesting to think about how long the signs of a star's death can remain visible. Some supernova remnants are still glowing thousands of years after the explosion. The famous Crab Nebula, for example, is the remnant of a supernova observed by astronomers in the year 1054. Nearly 1,000 years later, it is still expanding and shining. So the story of a giant star does not end with the explosion. It continues in the slow evolution of the remnant, in the gradual mixing of material into the galaxy, and in the eventual formation of new stars and planets from that enriched matter. This long, extended aftermath contrasts with the brief, intense moment of the explosion itself. It is another example of how different timescales coexist in the universe, from fractions of a second to millions of years. Another subtle aspect of this fate is how it changes the star's immediate environment. A supernova can dramatically reshape the region around it. The shock wave can compress nearby gas clouds, triggering the formation of new stars. At the same time, it can also disperse material, preventing star formation in other areas, so the death of a giant star can act as both a creator and a destroyer, depending on the context. This dual role adds to the sense of these stars as powerful agents in the galaxy. They are not just isolated objects. They are part of a larger system of interactions that shape the structure and evolution of galaxies. There is also the matter of how we, as observers, experience these events. Most supernovae we see are in distant galaxies. They appear as new points of light that fade over weeks or months. In our own galaxy, supernovae are relatively rare, occurring perhaps a few times per century. When one does happen, it can be a spectacular sight, visible even in daylight for a time. The last supernova observed in the Milky Way occurred in the early 17th century, long before modern astronomy. Since then, we have been waiting, watching stars like Betelgeuse and others, knowing that at some point one of them will reach the end of its life. This waiting adds a quiet sense of anticipation to the study of massive stars. Astronomers track their behaviour, looking for signs of instability or change that might hint at an impending collapse. But even when a star shows dramatic variability, it does not necessarily mean the end is near. Stars can be unpredictable, and the final stages of evolution are complex. So the fate of the universe's giants remains in many ways a story that is still being written. Another interesting thread to follow is the connection between these endings and the formation of some of the most exotic objects in the universe. Neutron stars and black holes are not just remnants, they are active, influential objects in their own right. Neutron stars can emit intense beams of radiation, produce powerful magnetic fields, and even merge with other neutron stars to create events that produce heavy elements like gold and platinum. Black holes can shape the space around them, accreting material and sometimes launching jets of particles that extend across vast distances. So the death of a giant star can be seen as a transformation rather than a disappearance. The star changes form, but it does not simply cease to exist. Its matter and its influence continue in new ways. From a reflective standpoint, this can add a gentle sense of continuity to the story. The universe does not waste what it creates. It recycles, reshapes, and reuses, even at the grandest scales. You might notice how the concept of a slow, dramatic fate resonates beyond astronomy. Many processes in nature involve long periods of quiet change followed by brief, intense events. A mountain can take millions of years to rise and only moments to collapse in a landslide. A forest can grow slowly and be transformed quickly by a fire. The pattern of build-up and release, of tension and transformation, appears again and again. In the case of the universe's giants, the build-up happens in the core, in the gradual accumulation of heavier elements, in the delicate balance between gravity and pressure. The release happens in the moment of collapse and explosion. But the story does not end there. The aftermath unfolds slowly, in the expansion of remnants, in the mixing of material, and in the eventual birth of new stars. So when we talk about the fate of the largest stars, we are really talking about a long arc that spans from quiet beginnings in dark clouds, through a brief, intense life of brilliance and size, to a dramatic transformation and a lingering legacy. This arc connects different parts of the universe across both space and time. It links the life of a single star to the evolution of a galaxy, and even to the conditions that make planets and life possible. It is a quietly thrilling thought. The idea that somewhere, far beyond the reach of our current maps and measurements, there might be a star even larger than the ones we have already met. A star whose light has not yet been studied in detail, whose size has not yet been pinned down with careful calculations, whose name has not yet found its way into books or quiet conversations about the extremes of the universe. The question itself carries a kind of open-ended promise. Could there be an even larger star we have not found yet? To begin exploring that, it helps to take a step back and think about how much of the universe we actually see. Our home galaxy, the Milky Way, contains hundreds of billions of stars. We have catalogued millions of them in detail, and we have rough measurements for many more. But even within our own galaxy, there are vast regions that are difficult to observe. Dense clouds of dust block visible light. Crowded star fields blur together. Entire sections of the galactic plane remain challenging to study in fine detail. And beyond the Milky Way, the scale expands dramatically. There are billions of other galaxies, each with their own billions of stars. The light from many of those stars is so faint and so distant that even our most powerful telescopes can only capture them as small, blended points. So when we ask whether there might be a star larger than UY Scuti or any of the other known giants, we are really asking how complete our view of the universe is. The honest answer is that it is far from complete. Astronomy is, in many ways, a science of sampling. We observe what we can, where we can, with the tools we have. From that sample, we try to infer what might exist beyond our current reach. In some areas, this works very well. The basic processes that govern how stars form and evolve appear to be consistent across different regions of the universe. The same physics that applies in our local neighbourhood also applies in distant galaxies. That gives astronomers confidence that they can make reasonable predictions about what kinds of stars might exist elsewhere. At the same time, there is always room for surprise. One of the factors that limits how large a star can become is radiation pressure. As a star grows more massive and more luminous, the light it produces pushes outward on the surrounding gas. This outward force can counteract gravity and make it harder for the star to gather additional material during its formation. In theory, this creates an upper limit on how massive a star can be at birth. If the star becomes too luminous too quickly, it will blow away the gas it needs to keep growing. This theoretical limit is often placed somewhere around 100 to 150 times the mass of the Sun, though the exact number depends on details like the chemical composition of the gas and the structure of the star-forming region. But mass is not the same as size. A star can have a moderate mass and still grow to a very large radius later in its life, as we have seen with red supergiants. So the question of the largest possible star becomes a question about how stars evolve, how much they can expand, and how stable they can remain when their outer layers become extremely extended and diffuse. The stars we currently know at the top end of the size scale are already pushing the boundaries of what stellar models predict. They are large, unstable, and often losing mass at a high rate. Their outer layers are only loosely bound to the star's gravity. This suggests that there may be a kind of practical limit to how large a star can become and still remain recognizable as a star, rather than dispersing into a cloud of gas. But that limit is not sharply defined. It is more like a region of uncertainty, where the balance between gravity, radiation, and mass loss becomes delicate. In some environments, especially in regions with lower amounts of heavy elements, this balance might shift. Heavy elements, in astronomical terms, are anything heavier than hydrogen and helium. They play a role in how gas absorbs and emits radiation. In regions with fewer heavy elements, the gas may be more transparent to radiation. This could allow a forming star to grow more massive before its light pushes material away. This is particularly interesting when we think about the early universe. Shortly after the Big Bang, the universe was composed almost entirely of hydrogen and helium. The first generation of stars, often called population 3 stars, formed in this chemically simple environment. Theoretical models suggest that these early stars could have been much more massive than most stars we see today, possibly hundreds of times the mass of the Sun. If that is the case, then the largest stars that have ever existed may have lived and died long before our galaxy even formed. Their light would be long gone, their remnants mixed into the fabric of the universe. We cannot observe these stars directly, because they existed in a time and place that is now far beyond our reach. But their influence may still be present in the chemical makeup of later generations of stars. So when we ask whether there could be an even larger star we have not found yet, we might be asking two slightly different questions. Could there be one out there right now, in some distant corner of the universe, still shining? And could there have been one in the past, larger than any we currently know, whose existence we can only infer indirectly? Both possibilities are open. Looking closer to home, within the Milky Way and nearby galaxies, astronomers continue to discover new massive stars and refine measurements of known ones. Space missions like Gaia, the James Webb Space Telescope, and others are improving our ability to measure distances, temperatures, and brightness with greater accuracy. As these tools gather more data, some stars that were previously underestimated may turn out to be larger than we thought. Others may shrink in the rankings as their measurements are revised. There is also the simple fact that some stars may be hidden. Dense regions of dust can obscure even very luminous stars in visible light. Infrared observations can penetrate this dust, but they are not always as precise in terms of spatial resolution. In crowded star-forming regions, multiple stars can blend together in observations, making it difficult to isolate and study individual objects. So it is entirely possible that there are giant stars tucked away in dense clusters or behind thick veils of dust that we have not yet fully characterized. Beyond our galaxy, the challenge becomes even greater. In distant galaxies, Individual stars are often too close together and too far away to be resolved one by one. Instead, astronomers study the combined light of many stars at once. This makes it difficult to identify and measure the size of a single, extremely large star in another galaxy. The light of that star is blended with the light of countless others. In some cases, astronomers can identify particularly luminous stars in nearby galaxies, such as the Large and Small Magellanic Clouds. These galaxies are close enough that individual massive stars can still be studied. In these neighbouring systems, astronomers have found some of the most massive and luminous stars known, and they continue to search for objects that might rival or exceed the giants in our own galaxy. So the exploration is ongoing, and the map is still being drawn. There is also a more philosophical layer to this question, one that touches on how we define the edges of what is possible. In science, every time we identify an extreme, the largest, the smallest, the hottest, the coldest, it acts as a test of our understanding. If we later find something that exceeds that extreme, it can reveal gaps in our models or highlight new physical processes. The search for the largest star is, in this sense, not just about finding a record holder. It is about probing the limits of stellar physics. What happens when a star's outer layers become so extended that gravity can barely hold them? How does mass loss behave in that regime? How does the star's internal structure respond? These questions do not just apply to one star. They apply to a whole class of extreme objects that help define the boundaries of what stars can be. There is also the question of stability over time. A star might briefly reach an enormous size during a particular phase of its evolution, then shrink or lose mass. If that phase is short-lived, the chance of observing it at just the right moment is small, so there could be stars that, at some point in their lives, become larger than any we have currently measured, but we simply have not caught them in that state. This adds a kind of fleeting quality to the idea of the largest star. The record holder might change not just because our measurements improve, but because the stars themselves are changing. Another angle to consider is the role of binary systems. Many massive stars do not live alone. They are part of pairs or even multiple star systems. In such systems, stars can exchange material. One star can transfer mass to another, altering both of their evolution paths. In some cases, this mass transfer can lead to one star becoming more massive or more extended than it would have been on its own. This could, in theory, create an unusually large star, one that pushes the boundaries of typical stellar evolution. There are also rare cases where stars in a dense cluster might merge, combining their mass into a single object. This kind of event is thought to be uncommon, but in extreme environments it might contribute to the formation of very massive stars. These processes add more complexity and more possibilities to the question of how large a star can become. From a more reflective perspective, there is something gently satisfying about the fact that this question does not have a final answer. The universe is not a closed book with all the pages filled in. It is an open story with new chapters being written as our tools and understanding improve. The idea that there might be something larger, something more extreme, waiting to be discovered keeps that story alive. It also mirrors the way human curiosity often works. We reach a milestone, celebrate a discovery, and then immediately begin to wonder what lies beyond it. In the context of the largest stars, this means that UY Scuti and its peers are not just objects of study. They are signposts pointing toward the edge of our current knowledge. They mark a place where our models, our measurements, and our imaginations meet. Another subtle point is how our sense of largest is shaped by the way we perceive and categorize the universe. We focus on individual stars, but in some ways the universe does not divide itself neatly into individual objects. Gas clouds, star clusters, and galaxies all blend into one another in complex ways. A red supergiant with an enormous diffuse atmosphere and a surrounding nebula can start to feel less like a single, well-defined object, and more like a region of space that happens to be dominated by a particular source of light and energy. So when we ask whether there could be an even larger star, we're also brushing up against the question of where a star ends and its environment begins. This is not just a technical detail, it touches on how we draw boundaries in our understanding of nature. As you sit with this idea, you might notice how it creates a kind of mental openness. The universe feels less like a list of finished facts and more like a landscape of ongoing exploration. There is room for new discoveries, new revisions, and new ways of looking at familiar objects. And even if the largest star we currently know remains the largest we ever find, the process of searching for something bigger has its own value. It drives the development of new instruments, new methods, and new theories. It encourages collaboration across countries and generations as astronomers build on each other's work to push the boundaries of what can be observed and understood. So in a way, the question itself becomes part of the answer. The possibility of an even larger star keeps the field moving forward. It keeps the night sky, which might otherwise feel static and unchanging, alive with potential. After all, whether or not there is a star larger than UY Scuti waiting to be found, the very fact that we can ask the question, that we can imagine such an object and look for it, says something about the human desire to explore, to measure, and to connect with a universe that is far larger than we are. There is a quiet moment that often arrives when you step back from the details, the measurements, the names, and the careful work of charts and calculations, and simply let the idea of these giant stars settle in your mind. Not as data points or record holders, but as immense glowing presences moving through the galaxy, living their brief, intense lives far beyond the reach of our everyday concerns. In that moment, the question of what they teach us begins to feel less like a scientific inquiry and more like a gentle reflection. One of the first lessons that tends to surface is about scale. It is one thing to know, in an abstract way, that the universe is large. It is another thing entirely to picture a single star so wide that it could stretch across the orbits of multiple planets, so vast that light itself takes hours to cross from one side to the other. That kind of size does not fit neatly into the mental boxes we use for most of our daily thinking. When you hold that image alongside the size of Earth, or even the size of the Sun, the contrast can feel almost surreal. Our planet, which feels so expansive when you travel across it, becomes a tiny speck. Our star, which dominates our sky and shapes our lives in countless ways, becomes a modest point of reference in a much broader landscape. This shift in perspective can be humbling, but it does not have to be diminishing. There is a difference between feeling small and feeling insignificant. Giant stars can make us feel small in terms of physical scale, but they can also highlight how remarkable it is that a small planet around a fairly ordinary star can produce beings who are capable of imagining, measuring, and wondering about such distant and enormous objects. In that sense, the existence of these stars reflects back on us. They're not just teaching us about the universe, they're also revealing something about the kind of creatures we are, curious enough to look beyond our immediate surroundings and try to understand things that have no direct impact on our daily survival. Another lesson that often emerges is about connection. It is easy to think of the universe as a collection of separate, isolated objects, stars here, planets there, galaxies scattered across vast distances. But when you follow the life story of a giant star from its birth to its death, a different picture begins to form. These stars are not just isolated points of light. They are part of a continuous flow of matter and energy. They form from clouds of gas and dust that were shaped by earlier generations of stars. They live for a brief time, shaping their surroundings with light, wind, and radiation. And when they die, they return their material to space, enriched with heavy elements, ready to become part of something new. That cycle connects everything. The carbon in your body, the oxygen you breathe, the iron in your blood. These elements were forged in the cores of stars long before the Earth existed. The giant stars, in particular, play a major role in creating and distributing these elements across galaxies. So when you think about a red supergiant swelling and eventually exploding, you're not just thinking about a distant spectacle. You are, in a very real way, thinking about part of your own deep history. This idea can bring a sense of belonging rather than separation. We are not outsiders looking in on a universe that has nothing to do with us. We are made of the same material, shaped by the same processes, part of the same long unfolding story. There is also a lesson in impermanence. The larger stars are, in many ways, the most fleeting. They live fast and end dramatically. They reach impressive sizes and brightness, but they do not stay there for long. In human terms, this can feel like a familiar pattern. Things that grow quickly and burn brightly often do not last as long as things that develop slowly and steadily. The universe seems to echo this pattern on a grand scale. Seeing this play out among the stars can make the idea of change feel more natural, less like an exception, and more like a fundamental part of how things work. Even the most massive and powerful objects in existence are not permanent. They have beginnings, middles, and endings. At the same time, their endings are not final in the way we often think of endings. When a giant star explodes, it does not simply vanish. It transforms. Its material spreads out, mixes with the surrounding space, and eventually becomes part of new stars and planets. So the lesson here is not just that things end, but that they change form. The universe is not a place where matter and energy are used up and discarded. It is a place where they are constantly recycled and reshaped. This can offer a gentle way of thinking about change in our own lives. Even when something feels like it's coming to an end, it may also be part of a larger process of transformation. Another idea that giant stars tend to highlight is the role of time. The timescales involved in their lives are both immense and, in a strange way, relatable. A massive star might live for a few million years. Compared to a human lifespan, that is unimaginably long. Compared to the age of the universe, which is measured in billions of years, it is relatively brief. This layered sense of time can make it easier to see how our own lives fit into a broader context. We exist on a timescale that is small compared to stars and galaxies, but large compared to many of the processes that shape our immediate environment. We live in a kind of middle ground, long enough to build histories, cultures, and stories, but short enough that change feels constant and sometimes overwhelming. Thinking about giant stars can stretch that sense of time outward. It can make a year, a decade, or even a lifetime feel like a small ripple in a much longer flow. That does not make those periods meaningless. It simply places them within a wider frame. There is also something to be learned from the way we study these stars. We do not interact with them directly. We do not touch them or travel to them. We learn about them by collecting light, by building instruments, by sharing data, and by refining models over generations. This is a collective effort. No single person can map the life of a giant star from start to finish. It takes the work of many people, across many years, often across many countries and cultures. In that sense, the study of these stars reflects a broader aspect of human society. Our ability to understand the universe depends on cooperation, on communication, and on the gradual accumulation of knowledge. Each observation builds on previous ones. Each new tool opens up new possibilities. The picture becomes clearer not through a single moment of insight, but through a long process of shared exploration. This can be a quiet reminder that some of the most meaningful achievements are not the result of individual brilliance alone, but of sustained, collective effort. Another subtle lesson comes from the way our understanding of these stars changes over time. What we thought we knew a few decades ago has been revised and refined as better data has become available. Stars that were once considered the largest have been surpassed or reclassified. Measurements have been adjusted, models have been updated. This ongoing process highlights the provisional nature of knowledge. In science, answers are rarely final. They are the best descriptions we have at the moment, always open to improvement. That attitude can be valuable beyond astronomy. It encourages a kind of intellectual humility, a willingness to revise beliefs in the light of new evidence, and an appreciation for the complexity of the world. There is also a lesson in how these stars are hidden as much as they are revealed. Many of the larger stars are wrapped in clouds of dust and gas, partly obscuring them from view. We see them through veils, in certain wavelengths, from certain angles. Our picture is always incomplete, shaped by the limits of our instruments and our position in the universe. This can be a gentle metaphor for how we experience many things. We rarely see the whole picture at once. Our understanding is often partial, influenced by perspective and context. Recognizing that can make it easier to approach the world with curiosity rather than certainty. On a more personal level, thinking about giant stars can invite a kind of quiet awe. Not the dramatic, overwhelming kind, but a softer sense of being part of something larger. It can be calming to realize that there are processes unfolding far beyond our immediate awareness, vast and slow, shaping the universe in ways that do not depend on our actions or our worries. This does not mean our lives do not matter. It simply means that they exist within a much broader tapestry. For some people, this perspective can be unsettling. For others, it can be comforting. It can make personal challenges feel lighter, not because they disappear, but because they are no longer the only things in view. There's also something to be said about the role of imagination. We cannot visit a giant star, we cannot stand near it or watch it up close, but we can imagine it. We can picture a sky filled by a vast red glow. We can imagine the slow movement of enormous convection cells across its surface. We can think about the moment when it finally collapses and sends its material outward into space. This ability to imagine things far beyond our direct experience is one of the ways humans connect with the universe. It allows us to bridge the gap between the small scale of our lives and the large scale of cosmic events. In that sense, giant stars are not just objects in space. They are also objects in the mind. They become part of our stories, our metaphors, our ways of thinking about size, time, and change. Another lesson that sometimes emerges is about rarity. The larger stars are not common. They form under specific conditions and live short lives. Most of the stars in the galaxy are small, dim, and long-lived. The dramatic giants are the exceptions, not the rule. This can be a reminder that what stands out most is not always what is most representative. The bright, impressive things tend to draw attention, but the quiet, steady ones make up the bulk of the universe. That does not diminish the giants. It simply places them in context. There is also a subtle connection between these stars and the night sky as we see it from Earth. Many of the bright, familiar stars we recognize in constellations are giants or supergiants. When you look up and see the red glow of Antares or Betelgeuse, you are looking at a star that has reached one of these later swollen stages of its life. So in a way, the story of giant stars is not just something that belongs to distant, obscure parts of the galaxy. It is written into the patterns we see overhead on a clear night. This can make the sky feel more alive, more like a place where stories are unfolding rather than a static backdrop. Another point worth reflecting on is how these stars help define the limits of what is possible in the universe. By studying the largest and most extreme examples, astronomers learn where physical laws begin to push back, where stability gives way to instability, where systems transition from one state to another. These boundaries are important. They help shape our theories and guide our search for new phenomena. In that sense, giant stars act like signposts at the edge of understanding. They mark places where our models are tested and sometimes challenged. This role can be seen as a metaphor for exploration more generally. Progress often happens at the edges, in places that are difficult to reach and hard to describe. Finally, there is the simple, quiet lesson of wonder. Giant stars are not necessary for our survival. We do not need to know about them to grow food, build shelters, or navigate our immediate environment. And yet, people across cultures and generations have invested time and effort into studying the sky, naming stars, building instruments, and sharing what they find. This suggests that curiosity itself is a fundamental part of being human. The desire to look up and ask questions, even when there is no practical benefit, is something that connects us to the broader story of the universe. So when you think about these immense distant stars, you're also thinking about a long tradition of curiosity and exploration that stretches back thousands of years. In that light, giant stars do not just teach us about physics or astronomy. They teach us something about ourselves. They show us that we are capable of reaching beyond our immediate world, of imagining and understanding things that exist on scales far larger than our own. They remind us that we are part of a universe that is both vast and intricate, and that our small, brief lives can still be connected to something much larger. As this reflection settles, it can leave behind a gentle sense of continuity. The stars will continue to form, swell, and fade long after we are gone. New generations will look up at the sky, ask their own questions, and build on what came before. And in that ongoing flow, our own moment of curiosity becomes one small part of a much larger, enduring story, one that stretches across space and time, linking the quiet glow of a distant giant star to the soft, thoughtful moment you are sharing with it right now. After spending so much time with the largest things we can imagine, it can feel almost like a gentle descent to bring attention back towards something closer, something quieter, something that fits into the space of a single night sky above your own head. The idea of drifting back down to Earth is not about leaving the giants behind, but about carrying what they have shown into a more familiar setting, letting that sense of scale and connection settle into everyday experience. If you were to step outside on a clear evening, or even just look up through a window, the sky might seem calm, still, and uncomplicated. A few bright points of light, maybe a faint band of the Milky Way if you are far from city lights, perhaps the moon or a passing cloud. It is easy to forget in that quiet scene that each of those points is its own sun, some small and steady, others vast and short-lived, some already gone by the time their light reaches your eyes. From this vantage point, the universe does not announce its extremes. It offers them quietly, wrapped in distance and time. There is something grounding in that contrast. On one hand, you have the image of a star so large it could stretch across planetary orbits, burning through its life in a few million years, shaping the galaxy with its light and its death. On the other hand, you have the simple act of standing still, breathing in cool night air, and watching a familiar pattern of stars that has looked much the same for generations of people before you. The giants are there, hidden among the points of light, but they do not demand attention. They simply exist, part of the same sky that has always been above human lives. This can make the sky feel like a kind of bridge between the immense and the immediate. You do not need to travel across light years to feel connected to what is out there. The light arrives on its own, quietly, every night. Another way to think about this return to Earth is through the idea of reference points. Throughout this journey, size has been a central theme. The size of stars compared to the Sun, the size of stars compared to planetary orbits, the size of stars compared to entire systems of worlds. Now, as attention comes back to the ground beneath your feet, the scale shifts again. The Earth, which felt so small when set against a red supergiant, becomes large and complex in its own right. Mountains stretch across continents, oceans cover most of the surface. Weather systems move and change, shaping landscapes over time. Within the context of a single planet, these are immense, powerful features. They shape the way life evolves, the way cultures develop, the way histories unfold. So scale is not just about size in an absolute sense. It is also about context. What feels small in one frame can feel vast in another. This can be a useful way to hold both perspectives at once. The Earth is tiny compared to a giant star, but it is the entire world for every living thing on it. Both statements are true at the same time. There is also a kind of comfort in returning to something that feels stable. The largest stars are dramatic and fleeting. They change quickly by cosmic standards. They end in powerful, sometimes violent ways. The Earth, by comparison, feels steady. It turns slowly on its axis. It moves gently around the Sun. Its changes, while significant, usually unfold over long periods. This sense of steadiness can be calming. It provides a backdrop against which the mind can rest, even while knowing that, on a much larger timescale, the Earth too is part of a changing system. Another aspect of drifting back down is noticing how the story of giant stars quietly weaves into everyday life, even if it is not obvious. The elements that make up the ground, the water, the air, and your own body were formed in stars that lived and died long before the Earth existed. Some of those stars may have been giants, shedding their material in winds and explosions that seeded the galaxy with the building blocks of planets and life. So when you look at something as ordinary as a stone, a leaf, or a drop of water, you are also, in a very indirect way, looking at the legacy of ancient stars. This connection does not require a sense of drama. It can be a simple, quiet recognition that the materials of everyday life have a deep and far-reaching history. Another way this return to Earth can feel grounding is through the idea of limits. The larger stars push against the boundaries of what physics allows. They test the edges of stability, mass and size. On Earth, we live within much narrower limits. There are ranges of temperature, pressure, and composition within which life can exist. There are constraints that shape ecosystems, societies, and technologies. Seeing the extremes of the universe can make these limits feel less restrictive and more defining. They are the conditions that make our particular kind of world possible. In that sense, the small sky is not a lesser sky. It is simply the one that belongs to us. There is also something to be said about the rhythm of attention. Looking outward, toward the largest and most distant things can expand the mind. Looking inward, toward the immediate and familiar can settle it. Both directions have their place. After spending time with ideas of vast size and dramatic endings, it can feel natural to let the mind come back to simpler images. A familiar constellation, the slow movement of the moon across the sky, the quiet hum of the world at night. These things do not compete with the giants. They coexist with them, each on its own scale. Another thought that can arise here is about perspective over time. The stars you see tonight will look much the same tomorrow night, and the night after that, and likely for the rest of your life. On human timescales, the sky feels almost unchanging. But on the timescales of stars and galaxies, the sky is in constant motion. Stars are born, grow, and die. Galaxies drift and merge. Light travels across immense distances, carrying news of changes that happened long ago. So the small sky above you is both a snapshot and a story in progress. This layered sense of time can add a quiet depth to the act of simply looking up. You're not just seeing what is there now, you're seeing a mix of moments from different parts of the past, all arriving together in the present. Another gentle lesson in this return to Earth is about presence. It is possible to think about the largest stars in the universe and still be fully present in a single moment. You can hold both ideas at once, the immensity of the cosmos and the immediacy of your own experience. This balance can be surprisingly calming. It allows the mind to expand without drifting away, to explore without losing touch with what is here and now. There is also a sense of continuity in realizing that the same sky you see has been seen by countless people before you. Ancient civilizations mapped the stars, told stories about them, and used them to mark the passage of time. They did not know about red supergiants or nuclear fusion, but they still felt a connection to the lights above. In that way, the act of looking up is a shared human experience that stretches across history. Another subtle point is how the language of largest and smallest can shift when you move between scales. On the cosmic stage, Earth is small. On the human stage, a city can feel large. On the personal stage, a room can feel like an entire world. All of these perspectives are valid in their own context. So drifting back down to Earth is not about shrinking the universe. It is about finding where you fit within it. There is also something to be said about the way the night sky can serve as a kind of mirror. When you look up at something so vast and quiet, it can create space for your own thoughts to slow down. The steady presence of the stars, even when you know how dynamic and dramatic they really are, can feel reassuring. It can create a sense of continuity, of being part of a world that has its own rhythms and patterns beyond the pace of daily life. Another way to hold this is to think about how the giants we have talked about will continue their journeys long after this moment. Somewhere, a massive star is shedding its outer layers. Somewhere else, another is nearing the end of its life, its core building toward a collapse that will send a wave of light across its galaxy. These events are happening whether or not anyone is watching. At the same time, here on Earth, someone might be making a cup of tea, turning off a light, or settling into bed. These small, quiet actions are happening whether or not anyone is thinking about stars. Both levels of activity are part of the same universe. There is a kind of gentle symmetry in that. Another thought that can come up is about curiosity itself. The journey from wondering what the largest star might be to reflecting on what that means for your own place in the cosmos is a path shaped by curiosity. That curiosity is not something that belongs only to scientists or astronomers. It is something that can arise in anyone who pauses and asks a question about the world around them. So in a way, drifting back down to Earth is also drifting back to that simple, human impulse to wonder. You do not need a telescope or a detailed understanding of stellar physics to participate in that. You just need a moment of attention. Another quiet connection between the giants and the ground is the idea of cycles. Stars form, live and die. Their material becomes part of new stars and planets. On Earth, water evaporates, forms clouds, falls as rain, flows in rivers, and returns to the ocean. Plants grow, shed leaves, and decompose. Rocks weather and become soil. These cycles are different in scale and in detail, but they share a basic pattern of change and renewal. Seeing that pattern in both the largest and the smallest things can make the world feel more coherent, more like a single system rather than a collection of unrelated parts. There is also the matter of light itself. The light from a giant star travels for thousands or millions of years to reach a telescope. The light from the moon takes just over a second to reach your eyes. Both are light. Both follow the same physical laws. The difference is distance and time. So when you see a faint star in the sky, you're connected to something very far away through the same basic phenomenon that lets you see the world around you. This can make the act of seeing feel a little more meaningful, a little more layered. Another gentle observation is about how knowledge and experience complement each other. You can know a great deal about giant stars, their sizes, their lifespans, and their fates. You can also simply experience the sky without thinking about any of that. Both approaches have value. The knowledge can add depth to the experience. The experience can ground the knowledge. So drifting back down to Earth does not mean letting go of what you have learned. It means letting it settle into a broader, more personal context. There is also a sense of belonging that can arise here. The Earth is not separate from the universe. It is part of it. The ground beneath you, the air around you, the water you drink, and the light you see all have roots in cosmic processes that stretch back to the earliest moments after the Big Bang. So when you stand under the sky, you're not just looking out at something external. You are, in a way, looking at a larger version of the same system you are part of. This can make the phrase "small sky" feel a little misleading. The sky may look small from the ground, framed by buildings or trees, but what it represents is vast. Another way to hold this is to think about how the sky can feel different, depending on where you are. In a city, it might be muted by lights. In a rural area, it might be filled with stars. In both cases, the same universe is there. The difference is how much of it you can see. This can be a quiet reminder that perspective matters, that what is visible depends on where you stand. As this return to Earth continues, it can also be an invitation to slow down. The larger stars move and change on timescales far beyond our own. They remind us that not everything needs to happen quickly. You can take a breath. You can let a thought unfold without rushing to the next one. There is no need to reach a final conclusion or a definitive answer. The universe itself is not finished. It is still unfolding, so it can feel fitting to let this journey settle into a kind of open-ended calm rather than a firm ending. The giants are still out there, swelling, shining, and fading in their own time. The Earth is still turning, carrying you through the night and into the day. The sky above remains, offering the same quiet invitation it always has, to look up, to wonder, and to feel, for a moment, both very small and very much a part of something far larger. And as that feeling lingers, it does not need to resolve into anything in particular. It can simply stay with you, like a soft awareness in the background, connecting the steady rhythm of your own breathing with the distant, ongoing rhythm of stars being born, growing vast, and eventually letting their light and their material drift back into the wide, patient space from which everything, in one form or another, seems to come.